Yeah, you're good.
Oh, perfect, perfect. All right, guys. So I got a webcam. I'm gonna see if it works. Try not to cringe too much, but let's see if it works. Oh, I see me. Do you guys see me too? I'm not sure if this adds to your learning experience, but here I am, in case you guys are wondering. And before we begin, I just want to go over some housekeeping, if you guys will, in E-class. So I'm assuming you guys can see my screen, of course, and we have our nice little E-class here. And there's a couple things I want to go over. The first is going to be there was a problem with the online textbook, but that's since been resolved, so it should be able to work now just fine. All right, yeah, so the online textbook, it now works. So if you guys were having problems with that, should be good to go now. As well, you guys were having troubles with Abacus. So I have a new Abacus installation guide. A lot of you guys said that this one does work. So if you guys want to install Abacus, this is the way to go. But don't worry about it too much right now. As you guys will see, we won't get into Abacus until about lecture 5. So you guys have plenty of time to download Abacus. It's not a rush or anything like that. For the first couple assignments here, we're mainly dealing with Mathematica because we are still more or less in the theory section. We haven't really got into the finite element program yet. All right, so today's lecture, as you guys can see, lecture 2, we have solid mechanics, and there's a lot to go over. So I'm going to be the first to just apologize to you guys. It is a lot to go over. This is why we have solid mechanics, or for you mechie kids, continuum mechanics. This is why we have it as more or less a prerequisite of this course. We're going to use it a lot. Therefore, we have a lot of content to review, even though you guys already know it. But if you guys don't know solid mechanics, as a lot of you guys have not taken it, we say it's a prerequisite, but we don't really enforce it too well. But if you guys haven't taken it, don't worry. I'm going to show you guys everything you guys need to know when it comes to solid mechanics. And then from there, as you guys can see, things start to get a little bit lighter per lecture. So this is going to be a heavy lecture. Yeah, an interesting lecture though, because solid mechanics is very nice and fancy and looks really sexy. But after that, things get a lot easier. So the workload starts going down and the topics start becoming more condensed. So if you guys can handle today's lecture, you guys will be able to handle anything. Now, we also have an assignment due next week. So I'm going to be going over assignment 1 here. Kind of in the third part of the lecture. So I split the lecture up into basically 1-hour sessions. The first session, we're going to go over displacement and strain, as well as the stress tensor. In the second one, we're going to go over the stress measures, balance equations, and constitutive laws. And then finally, in that third hour, we're going to look at Euler-Bernoulli beams. Now, if you guys have already looked at the assignment, Euler-Bernoulli beams, that's basically the assignment. So the whole assignment can be done if you guys know Euler-Bernoulli beams. And because it is an assignment question, we're going to go over an example. So hopefully by the end of the example, you guys will know exactly what to do on the assignment. It should be a nice, easy time. My job in this in this class is to make it easy for you guys. I don't want you guys thinking, oh, finite element it's not a fun class. I want this to be a nice, easy class for you guys. So hopefully we can keep it as easy as possible, and hopefully the examples will show you everything you guys need to know. But again, we'll go over the assignment just to make sure that everything is flowing well. All right, guys. So do you guys have any questions before we begin, or is everything good so far? Hopefully good so far. I have the chat up, so if you guys just want to type in the chat, or again, sometimes I can't see chat, so if you guys just want to unmute yourselves and interrupt me, please do that. I'd prefer that than you guys waiting on your question. All right. So let's begin with our first topic, which is the strain tensor. So it says the strain tensor, but remember, in this particular class, due to what we are working with, which is basically reality, we can say the strain matrix. Strain tensor, matrix, in this course, they're more or less interchangeable. There's only going to be one real part where the fact that we're dealing with a tensor comes into play. However, it's more theoretical. You guys won't really need to know the implications or anything like that. So let's begin by talking about configurations. So if I were to have a potato, okay, just a regular potato on a page, well, it really means nothing to us. We don't have any sort of mathematical preliminaries to describe what this potato is. So what we do is we actually put a bunch of points on the potato, and we call it material points. And the way that we do this is, or why we do this is, we can start embedding things into R3. How do we do that? Well, we introduce a reference configuration. So in the last lecture, we talked about basis sets. So every time we have a basis set, it's basically our coordinate system, if you will. So we're going to introduce a coordinate system in 3D with basis vectors e1, e2, and e3. Now this is particularly important because every point on that potato we now can represent as a vector. So in this particular picture here, I only have 3 points represented by 3 vectors. However, we would represent this potato or any other shape in 3D or 2D as a series of infinite points. Therefore, we have an infinite amount of vectors. So therefore, we can represent this potato as basically a collection of vectors. Now, if we look at these vectors, since we're dealing with an orthonormal basis set, each one of these vectors can be written as a linear combination of the basis set. So if we had a vector x, we can just write it as x1 e1 plus x2 e2 plus x3 e3, basically the components in each direction. All right, and the collection of vectors, because again, we have many vectors here representing this potato, the collection of these vectors is referred to as the reference configuration, or omega naught. Now, this is before any deformation happens, and that's going to be the key. But of course, when we're looking at this coarse finite element as a whole, we know that we're actually going to deal with deformation. We're going to actually have to make some modifications for that. So far we discussed we have a potato, it has a bunch of material points, and it has a reference configuration omega naught. Now, each vector from basically the origin of the coordinate system to these points, we're going to represent by a vector big X. Why big X? Well, we're actually going to have a second vector called small x a little bit later. So let's say we take our potato and we deform it. All right, so we're going to deform it by a function f, such that x is equal to f of x. Now from this, we can see that our potato has rotated a bit, it has stretched a little bit, stuff like that. Now, what we're going to look at is how that point changed, because that blue point, that is the exact same point on the potato. What we're going to want to do is try and figure out a correlation between that reference configuration as well as the deformed configuration. All right, so the first thing that we have to do is we have to look at how we transformed this potato, that function f. Well, what we're going to do is we're going to assume that f is bijective, and if you guys remember from the linear algebra review, that basically means that f is invertible, meaning that if I have the deformed configuration, I can go back to the reference configuration if I wanted to. We also assume that f is continuous, as well as smooth, which basically means that it's going to be differentiable. That's going to be one of the big key things here when we start looking at solid mechanics, is that everything can be differentiable. Now, is everything differentiable in real life? No, not exactly. And that is actually why we need the finite element method. So we haven't got to the finite element method at this point. What we're going to do is we're going to look at the theory, basically looking at how do we obtain an exact solution. And from there we can realize, oh, well, we can't always obtain the exact solution. And that's why we use the finite element method. All right, so now that we have deformed this by displacement function f, we can define a second vector. All right, so remember we had that original green vector, which is big X, which goes from the origin of the coordinate system to the point in the reference configuration. Well, now we have a second vector, which goes from the origin to the point in the deformed configuration. And what we call this point is the position function small x. All right, so we have what I like to call big X, which is the vector to the reference configuration, and then we have small x, which is a vector to the deformed configuration. All right, so again, that small x, we call that the position function, and it's going to be very important moving forward. Now, we can also define a third vector. All right, so we have a second vector function that relates the displacement of the particle in the current position to the reference configuration. So you guys may be saying, Clayton, that's a bunch of words. I don't like words. Just show me what that means. Well, I'm saying I can define a third vector that goes directly from the point in the reference configuration all the way over to the point in the deformed configuration. Now, what we do is we call this vector u, which is called the displacement function. So you guys are going to hear two functions: position function, which is going to be that small x, and displacement function, which is going to be ux. Now, if we were to take a step back and look at our little schematic here, we basically have vector addition. All right, we have the hypotenuse vector, which is the purple one, and then we have the two side vectors, which is the green one as well as the red one. So it's actually very easy to see a nice relationship where our displacement function u is actually going to be equal to our position function small x minus big X. All right, so this is going to be the key here, this little relationship where u is equal to small x minus big X. Now let's discuss exactly what this means and try and illustrate what it means. Because if I look at this now, it definitely looks confusing. Let's go through some examples. So the first one we're going to look at is rigid body displacement fields. Rigid body is perhaps the easiest thing to picture. As you guys may have guessed, rigid meaning nothing deforms. All right, so we're not looking at deformation yet. We're just going to look at simple translations and rotations. So the first one that we have is rigid body displacement. And in this case, my position function small x is going to be big X plus c. Now you guys are going to say, oh, hold on, what is c? I don't remember you showing me a c. Well, c is just a constant vector. So it could be, let's say, 1, 1, 2, 4, negative 5, 2, something like that, just a constant vector. And the reason why it's written like this is because if we were to look at the displacement function u, which is going to be x minus big X, well, we can see that the big X cancels, and our displacement function u is actually just equal to c. And what this means is that every point on that continuum is going to be translated by a value of c. So if we had a plate in two-dimensional space and we were to go over rigid body displacement, again, all we're doing is we're taking every point on that plate and translating it by an equal amount. So our plate will end up, let's say, somewhere over here. But if we look at the plate, we notice two things. One, it has not rotated yet. Kind of a spoiler alert for what's coming up. But we also see that it hasn't deformed. So it hasn't stretched, it hasn't expanded or contracted. None of that yet. And that has to do with it being, of course, a rigid body. Now, the second thing that I alluded to is rigid body rotation. Now, in this particular case, our position function is going to be q times x, where q is that nice rotation matrix that we discussed last lecture. So you guys know all about q already. Now we can figure out the displacement function u, which is small x minus big X. Therefore, we get our displacement function to be q minus I times x. And what this is basically doing is it's just rotating our plate. So if we were to look at our plate and we were to apply a rotation matrix, what we can see is that it simply just rotates by a certain amount of theta counterclockwise. Now, another thing to keep in mind, again, we haven't induced any strains into this plate. It hasn't expanded, it hasn't contracted, anything like that. So we just rotated the plate, but we haven't translated it. So the third one, as you guys can imagine, is called rigid body motion. This is the one you guys have probably heard the most. And it's basically just a combination of 1 and 2. So our position function can be qx plus c. Therefore, our displacement function can be q minus I times x plus c. If we were to take our plate and apply this displacement field to it, well, what we can see is we both rotate our plate as well as translate it. But again, we have not dealt with any sort of strains up until this point, or any sort of deformation. So now let's look at some of the simplest cases of deformation, which is uniform extension and contraction. Or you can say expansion, doesn't really matter too much. The key for this one is it's going to be characterized by 3 positive parameters. All right, we got K1, K2, and K3. So uniform extension and contraction, our position function is simply going to be a matrix multiplied by big X, which is the matrix is going to be K1, K2, and K3 as diagonal components. Therefore, our position function small x is going to be K1, X1, K2, X2, and K3, X3. From this, we can calculate our position function u, which is equal to small x minus big X, and we get that our displacement function is going to be K1 minus 1 times X1, K2 minus 1 times X2, and K3 minus 1 times X3. Now again, this is just a bunch of fancy math. If we want to see what this actually represents, let's look at our 2D plate. And let's play around with some of the parameters. So since we're keeping this in 2D, we don't have a K3. K3 has to do with that direction E3, which we don't have in this particular case. So what we can do is we can play around with K1 and K2. So let's look at the first scenario, where I take both K1 and K2 greater than 0. So if I look at this, I can see that my plate, if I apply this uniform extension and K1 and K2 are greater than 0, my plate starts to expand in both of those directions. So K1 is greater than 1, we can see it expands horizontally. K2 is greater than 1, we can see that it expands vertically. Now what we're going to do to illustrate what we can do with these k parameters is we're going to play around with k1 at the bottom there. So right now we have k1 is greater than 1, but if I wanted to, I can change k1 to equal to 1. Now this is a very nice case because if we look at this, we see that we actually don't have any expansion or contraction in this case. The length in the horizontal direction does not change if k1 is equal to 1. Now on the other hand, what we can do is we can take k1 to be less than 1 but greater than 0. If this is the case, we can see that we now have contraction rather than expansion. So k here actually leads to 3 different scenarios. The first one is contraction if k is between 0 and 1. The second one is expansion or extension if k is greater than 1. And then the third one is there's no change in length if k is equal to 1. All right, so if we look at this and you say, oh, hold on, Clayton, 1 second. What if k is equal to 0? Or what if k is equal to a negative value? If we look here, the only physical possible values that we have right now is k is a positive number. Well, what happens if k is equal to 0 or k is less than 0? The object actually inverts upon itself. So if we were to look at that green point there and I were to apply this transformation, we can see that the object basically becomes inside out. Now, it's not the best way of describing things, but you guys can probably picture what's happening. And we note that an object can't just invert upon in itself. It's not physically possible. So mathematically, we can have negative values of k, no problem at all. With math, we can make anything work. However, it's not physically possible. So if it's not physically possible, well, it really defeats the purpose of this course. So we don't really deal with k is less than or equal to 0. And the reason why, the object inverts upon itself, or basically it becomes inside out, if you guys will. All right, so that's uniform extension and contraction. The next thing we're going to talk about is shear. So we basically have 2 types of shear. The first one is simple shear, and our position function can be described as simply x1 plus tan theta x2 plus, and then x2 and then x3. Now this is what shear is, because if we look at our displacement function, which is small x minus big X, we have tan theta x2. Now this is particularly fascinating because if we look at the displacement function u1, which is in the horizontal direction, we can see that it's actually a function of x2, which is the vertical direction. So that's going to be the key thing about shear here. What does this look like? Well, if we have a plate here and I were to subject it to this displacement field, we're going to see something like this. So this is going to be something you guys see a lot when we're talking about finite elements. We refer to this more as distortion. So if we were to look at this, we see shear, which basically means the further up we go along this plate, the more it's going to displace horizontally. All right, so that's the first case, which is simple shear, but we also have a second case called pure shear. Now, pure shear is very similar to simple shear in the fact that we're dealing with tan of theta, but instead of just having it as one component in our matrix, we actually have it as 2 components. All right, and because of this, we get our nice position function x1 plus tan theta over 2 x2, tan theta over 2 x1 plus x2, and then x3. So from this, we can calculate our displacement function as simply tan theta over 2x2, tan theta over 2x1, as well as 0. So again, if we look at here and look at our displacement in the horizontal direction, it is now coupled with the vertical direction. And vice versa. If I were to look at the displacement function in the vertical direction, it is now coupled with the horizontal direction. What does this look like? Well, if I have my plate and I apply this particular displacement field to it, we're going to get something like this. So of course, the more horizontally we go throughout the plate, the displacement's going to go up. And the more vertical we go throughout the plate, the displacement's going to go more horizontally. So hopefully that shows you guys what exactly shear is. So that was my little brief introduction into displacement functions as well as position functions, basically small x and u. Those are going to be very important once we start talking about strain here. All right, strain is kind of the meat and potatoes of this entire lecture. If you guys can get strain here at the beginning, the rest of the lecture is going to be a piece of cake for you guys. So how do we describe strain, or how do we derive strain? We go back to our figure. So remember that in our figure, we basically had a potato. It was in a reference configuration and it had a blue point on it. This blue point was described by a vector big X, and then what we did is we deformed the potato. In the deformed configuration, the blue point is now described by a vector small x, and then we have a nice red vector between them, u of x, which relates the 2 points in the reference and the deformed configuration. Now to describe or derive the strain tensor here, or strain matrix, what we're going to do is we're going to introduce a second point. So in our reference configuration, we have a vector that goes from the first point to the second point, and it's going to be described by a vector d big X. All right? And in the deformed configuration, we're going to have a vector that describes the 2 points as d small x. Now this is going to get really confusing, of course, if I were to say big X, small x. So I'm going to make it very clear for small x. If I'm ever referring to small x, I will say small x. If I were to just say dx though, and just x by itself, I'm referring to big X. All right? Now, I'm going to tell you guys really quick. The goal of this course is in solid mechanics. We're looking at the finite element method. Everything I'm presenting to you guys right here is just going to be a derivation. You guys will not be tested, I promise you guys, on any sort of derivation in solid mechanics. Okay, that was the goal of solid mechanics. That's not the goal here. So if you guys are looking at this derivation going, you know what, Clayton? Derivations kind of suck. I don't want derivations. Don't worry. I'm not going to test you on derivations of solid mechanics. That's outside the scope of this course. All right, so don't worry about it too much. So now what we're going to do is we're going to look at those 2 new points that we created, the light blue points, and we're going to create a second displacement function that relates them. So instead of u of x, it's going to be u of x plus dx. All right, and here's going to be the key. And this comes from vector addition. What we're going to want to do is we're going to want to create 2 paths. We're going to want to create a path from point O, which we can see is down at the origin on the left-hand side, to point P, which is that second point in the deformed configuration. All right, and if we look at this, we can say, well, we actually have many different path options. Let's look at path number 1. What I can do is I can go up x, then up dx, and then across by u of x plus dx. All right, vector addition, that works out just fine. I end up at point P. Now, you guys may be saying, Clayton, that's the long way. Why would you want the long way? Let's look at the short way. Well, instead of saying that path number 1, let's go path number 2, where I go across small x and then up d small x. All right? Now, the key here is that by vector addition, these 2 paths are actually equal. It's path independent. Therefore, we can equate these 2 paths. So from there, I get small x plus d small x is going to be equal to big X plus d big X, u of x plus dx. All right? Now from here, this is where we start deriving everything. It's this equation right here. It's going to be somewhat special to us. So the first thing I can say is, hold on a second. I have a small x and I have a dx. Now, if we remember from the previous slides, there's a nice relationship between small x and big X, as well as the displacement function. So what I'm going to do is I'm going to take that small x on the left-hand side, and I'm going to throw it over to the right-hand side, and I get this right here, where I get minus small x minus big X. Now, if you guys remember from the first slide, we said this is actually a very specific property, that small x minus big X, that's actually a displacement function. So that's simply u of x. So from here, I got d small x is equal to d big X plus u of x plus dx minus u of x. Now, this is something that's a little bit outside the scope of the course. That's why I haven't really covered it. But this right here, this u of x plus dx minus u of x, this is actually something very special. If you guys go into vector calculus or tensor calculus 2, you guys will know that this is actually referred to as a gradient. So more specifically, we can simplify this into d small x is equal to dx plus nabla u, which is going to be our displacement gradient. That nabla u, or that upside down triangle, that's our displacement gradient times dx. All right, so that's our displacement gradient. Now, if I were to look at this, I say, hold on 1 second. I have dx basically in both my terms. So what I'm going to do is I'm going to factor out the dx, and I get d small x is equal to I plus nabla u times d big X. All right, now I already surprised you guys with nabla u. I kind of caught you off guard there. I'm going to do it again. Now, I'm not trying to be an ass. I'm just showing you guys the proof. So what happens is there's actually another relationship called the deformation gradient. So remember that nabla u above, that's our displacement gradient, but we also have something called the deformation gradient, which is f. And f is equal to I plus nabla u. Now, the reason why we're doing this is because we can simplify the equation to d small x is equal to f times dx. All right? So this is going to be the equation that we're going to work with when it comes to strains. The reason why is because remember that strains are basically the change in length of something. So if I'm looking at my original position between those 2 points, I have a vector dx. From dx, I can find the distance between those 2 points in the reference configuration. Now, in the deformed configuration, I still have the same 2 points, but they're represented by a vector d small x. But again, from d small x, I can find the distance. So what this equation down here actually tells me is how the length of those two vectors, those two vectors, how they change after the deformation. All right, and this is what we're going to build upon. But first of all, we have to clear up the thing I caught you with off guard, which is the deformation and the displacement gradients. I said that there was two things. We had nablu as well as f. So let's try and clarify those so there's no confusion moving forward. First one, the displacement gradient, which is nablu. And since since u, our displacement function, is a vector valued function, the gradient of u, which is nablu, is actually going to be a tensor field. Now what this fancy statement says is that since u is a vector, the gradient is going to be a matrix. All right. Now, we're not going to get into where this comes from because this is even outside the scope of solid mechanics. Really, this is more tensor calculus. But basically, nablu is equal to the partial derivative of ui with respect to xj, big xj. Now, what this is actually going to do in our 3 dimensions is create a matrix. Now, if I'm looking at this, I'm thinking, this looks absolutely horrendous. I want nothing to do with this. And this is where you start scaring all the undergraduate students. I throw this at the undergraduate students. They don't like me anymore. But you guys are much smarter than them. So you guys are going to realize, hey, this is actually not too bad. Because what we're basically doing is we're taking our displacement function, u1, u2, u3, and we're just taking the partial derivatives with respect to x1, x2, x3. For instance, if we were to look at this first column here, it's always u1. You see that in the top, or the numerator of all those fractions, it's always u1, u1, u1. So the first row always has to do with u1. And all we're doing is taking the partial derivative with respect to x1. That's our first component. We take the partial derivative with respect to x2. That's our second component. Then we take the partial derivative with respect to x3. That's our third component. So all we're doing is taking partial derivatives. It's nothing too crazy. We look at the second row. Well, it's the same thing as the first row, but instead of u1, now we're looking at u2. And finally, for the third row, instead of looking at u2, we are now looking at u3. All right, so even though it looks really bad, quite simple. The second thing that I threw at you guys was the deformation gradient f. Now, f is actually going to be very similar to nablu, and that we already said that f is equal to I, which is the identity matrix, plus that nablu. So from there, I can write out the identity matrix, which is simply a diagonal matrix full of ones, plus nablu, which we defined above, and we get the following, where it's basically equal to the exact same thing as our displacement gradient, but instead of taking the partial derivatives of the displacement functions u1, u2, and u3, we're taking the partial derivatives of the position functions. So instead of u1, u2, u3, we're actually dealing with x1, x2, x3, or I should be more clear, we're dealing with small x1, small x2, small x3. So in essence, the deformation gradient is the partial derivative of small xi with respect to big xj. So it's just the gradient of the position functions. Nice and easy, right? Or at least, hopefully. Now, since we defined these, we can now go back to our nice equation that we had before, and we are now going to derive the green strain tensor. Now, the green strain tensor, this is the big boy of the course, if you will. This is going to be one that is very important to know, but we don't really use. And we're going to describe why we don't use it as much moving forward. So remember that we left off with the following equation where we had the vector dx, which is the vector between the 2 points in the deformed configuration, is equal to f times d big X, where dx is the vector between the 2 points in the reference configuration. Now again, we said that we're trying to focus on strains. We're trying to deal with strains in this course, which is the change in lengths. Now, question for the chat over here. I guess I have it written down, but I was going to say, how do we get the length of a vector? But you guys already know that because I have it written down. I should have asked you guys before I clicked the button. But basically, if we want the length of a vector, the distance between those 2 points in a vector, we take the norm. All right, so this is going to be the key here. Again, when we're dealing with strains, we want the change in length. And if I were to look at this equation, we have vectors. So what I want to do is I want to modify the equation above to give me lengths of the vectors rather than just the vectors themselves. So what I'm going to do is I'm going to dot both sides of that equation with itself. So instead of dx is equal to f d big X, I'm going to have d small x dot d small x is equal to f dx dot f dx. And you're going to say, Clayton, that just looks like you just did more work. Why would you do that? Well, remember, when we're talking about norm, if we have a vector dotted with itself, it's actually equal to the norm of that vector squared. So now I have the norm of d small x squared, which is basically the length or the distance between those 2 points in the deformed configuration squared. So I now have a distance on the other side. Now on the other side, I have d big X dotted with f transpose of f times dx. And this is going to be the key here. So what we're going to do is we're going to take that component f transpose of f and we're going to call it C, where C is defined as the right Cauchy green deformation tensor. Now that's a mouthful. Don't worry about that one too much because we're not going to deal with it too much. It's just more for the purposes of derivation. So now what I'm going to do is I'm just going to assume something, right? You guys know how much fun it is to assume something. So what we're going to do is let's just say, so it's not always the case, but C, which is equal to f transpose of f, is equal to the identity matrix, all right? Equal to the identity matrix. Well, then we just have d big X dotted with d big X, which is just going to be the norm of dx squared. So if I were to look at the equation, it's basically we have the norm of dx squared is equal to the norm of d big X squared, which means that the length does not change. All right, so this is going to be the key here. If that Cauchy green deformation tensor is equal to I, the length does not change. And we can see that mathematically in our equation here. Now, what we're going to do is we're going to take C, f transpose of f, and we're actually going to expand it out by definition. So remember that f is equal to I plus nably u. All right, so from there we can expand it out and we get this big long equation here where C is actually equal to I plus nably u plus nably u transpose plus nably u transpose multiplied by nably u. Now, the reason why I showed you the statement above is if we look at this component here of C, or the whole thing is C, well, we know that that I that's in that equation, that has to do with rigid body motion. So if we get C is equal to I, we have rigid body motion. Therefore, if we have rigid body motion, all of those terms have to be zero. Now, what's going to happen when we start dealing with displacements and strains? Those terms will not be equal to zero. So therefore, those terms right there, that nably u plus nably u transpose plus nably u transpose nably u, these are what are going to cause the strains in our continuum. All right, so these are the ones that we're going to focus on. So now let's redefine our right Cauchy green deformation tensor as follows, where C is equal to I plus 2 times the green strain tensor. All right, so the whole goal of this lecture was to find the tensor. We now have the tensor. So we have our green strain tensor as 1/2 of nably u plus nably u transpose plus nably u transpose nably u. We call this the green strain tensor. So we're going to define it. So any equation that I box in the black box, that's probably one of the ones that's good to know. So now we've derived the green strain tensor. And if you guys are saying, you know what, Clayton, I'd rather have it in component form, well, no problem at all. There it is in component form. It's not very nice looking, as you guys can imagine. Now, this tensor has very specific properties. The first one is symmetric, which is great for us. We talked about symmetric tensors. It basically means that our calculations are going to be easier, especially when we start talking about approximations. Now, the key here for us as civil engineers or mechanical engineers is this tensor is going to be valid for finite deformations. All right, finite deformations. So no matter what situation you guys find yourself in, this tensor is actually valid. All right, so that's going to be the green or the Lagrangian strain tensor. We have a nice formula here. So if we know our displacement gradient, nably u, we can calculate the tensor no problem. How do we get nably u? Oh, well, we needed the displacement function. So basically, if I have a displacement function, I can find the strains associated with that displacement function. Now, if you guys are worried about the derivation, again, please don't. This course is not about derivations. It's showing you guys where it comes from so that when you guys use it in practicality, you guys know, oh, I know generally where this comes from. It's not so much of a mystery. Now, I got good news for you guys. we're not using this green strain tensor often. I told you guys that this is something that's good to know, very powerful, but we're not going to use it that often. Instead, we use what we call the small or the infinitesimal strain tensor. All right. The reason why? Well, that green strain tensor, as great and sexy as it is, it's valid for finite deformations, which sounds great, right? Like, oh, finite, I can use it in any scenario. It's perfect. However, in most applications, we deal with small deformations. Now, this is a civil engineering course, so in civil engineering, we deal with small applications. When I say that in most applications we deal with small deformations, I'm probably making the mechie kids cringe probably a little bit, but remember that this is a civil class. This is why I'm saying that we have these small deformations. So when we look at a green strain tensor, remember, it's valid for finite, large deformations. However, since we're only dealing with small deformations, what we can do is we can actually look at that last term there and say, well, actually for small deformations, that nablu transpose nablu, that's actually going to be much smaller than the component nablu itself. Therefore, we're going to say that that last component there is it's approximately equal to 0. Therefore, our green strain tensor is approximated as 1/2 of nablu plus nablu transpose. This modified strain tensor that we now have here, we call this one the small strain tensor. Therefore, when we're dealing with applications here in finite element mechanics, stuff like that, we're usually going to be referring to this small strain tensor, which can be calculated as simply 1/2 of nablu plus nablu transpose, or if you guys want it in component form, it looks much nicer than the green strain tensor. Now, again, it has some nice properties. The first one is this one will also be symmetric, which is great. However, this is valid for small deformations. But when we're dealing with civil applications like buildings and beams, that assumption is perfectly fine, because if your building's deforming a lot, well, you have a bigger problem. Who cares about the strain tensor? Let's be more concerned about the building itself. So that's really it for the strain tensor. How are you guys feeling? This is the hardest one. So if you guys know the strain tensor, the rest of the lecture is just going to be a piece of cake. You guys feeling good so far? Again, just know the final formulas. You don't really need to know the derivation too much for this course. All right, I'll take the lack of messages, or the outstanding silence as we're good to go. Perfect. So now we're going to get on to the Cauchy stress tensor. This one's going to be a little bit shorter than the strain tensor, which is good. The strain tensor is a little bit long. So let's talk about the Cauchy stress tensor. So we went from strains. Now we're going to talk about stresses. So the first thing we're going to talk about is actually called a traction or a stress vector. So let's say that I had a bar. What I'm going to do is I'm going to cut this bar in half. So I go snip, 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 and I'm left with basically 2 bars. Now, as you guys remember from statics all the way back into the first year of your undergraduate careers, when we cut something, we release internal forces. But the first thing that we have to get to before we talk about those internal forces is our cutting plane. So what we're going to do is define how we cut it, because again, I cut it vertically, but it doesn't have to be vertically. I could have cut at a diagonal if I wanted to. So what I'm going to do is I'm going to define a normal vector. Now, the whole purpose of this normal vector is that it's going to be perpendicular to my cutting plane. So basically, it defines my cutting plane. Now again, we cut it, we expose the internal forces. So what happens is when I cut this in half, I have a bunch of internal forces going everywhere, and in its current state, it's actually it's a mess. No one likes it right now. So what we're going to do is we're going to define an area delta A, and we're going to take all of those forces that are in that area delta A, and we're going to sum them up into one nice force delta F. All right, so that delta F there, it's a vector. Delta A, it's simply just an area. So what we're going to do is we're going to define a traction vector, or the stress vector at a point on a surface surrounding the point, with a normal vector n as the limit as delta F divided by delta A basically goes to 0. All right, and if we were to look at these two figures above, we can impose Newton's law of motion, which basically says that the traction vector on the left-hand side is going to be equal to the traction vector on the right-hand side, just opposite in direction. All right, so nothing too crazy here. Now, you guys may be wondering, traction vectors, what basically is this? Well, I just want you guys to think of traction vectors like this, because that right there, that's the formal definition, and no one likes the formal definition. Basically this: if I were to take a beam in statics and chop it up, I have my shear, I have my normal force, and I have my bending moment. basically what we're dealing with now in these 3D objects is when I cut my beam, I basically have a vector of stress components. All right. So that's what I'm dealing with here is when I cut something, I now have stress components. Now, we're going to talk about this traction vector, try to make it a little bit easier. How are we going to do that? Well, we're going to go back to our friend, Mr. Potato. So what we're going to do is we're going to extract a little infinitesimal sized cube from this potato to show you guys exactly what traction vectors are. So since this point is inside the continuum, what we're basically saying is that traction vectors are just the stresses on each surface of this point. All right, so each face of this cube has a traction vector. If I look here, I say I have TE1, TE2, and TE3, which is basically the stress vector on each face of this cube. Now the goal here is to try and figure out what exactly is this traction vector. What are these stress components? So what we're going to do is say, hold on a second, if I were to look at this cube, it's looking really good in the sense that each face is perpendicular to one of the basis planes. All right, so what I'm going to do is instead of TE1, TE2, TE3, I'm actually going to split it up into components, and the components are going to be aligned with my basis vectors. All right, so if I were to look at the purple surface over here, I can see that my traction vector TE3 can actually now be written as a linear combination of those basis vectors. So instead of just TE3, which was unknown to us, basically we have sigma 3(1) times E1. So this is going to be my stress component in the E1 direction, plus sigma 3(2) times E2, so my stress component in the vertical direction, and then sigma 3(3) times E3, which is my stress component along the E3 axis, or in the second vertical or horizontal direction, I guess. So this is what a traction vector is. It's just the stress components on a face of a cube. Nothing too crazy. Now, we can look at this formula and say, all right, well, that's just for that one particular face. But in general, we can have a traction vector on a surface perpendicular to the basis vectors as TEI is equal to sigma ij times EJ. Now, this is written in that Einstein notation. So if you guys are not familiar with that, there's basically a summation of 1 to 3 in there over J. All right, so it looks a little bit confusing, but it's not too bad. The whole point here is that on each face of the cube, we have a stress vector. That's all you guys really need to know. Now, if we were to look at this cube, we say, all right, it's very, very simple to determine what those stress components are if our surface is aligned with those basis vectors. If we look at the cube here, all those surfaces are nice and perpendicular. They almost form an orthonormal basis. Like, it looks very, very nice. So what we're going to try and do, and the whole point of the Cauchy stress tensor, is to try and figure out what this stress vector is on an arbitrary face. So we have it if it's aligned with the basis vectors, but we don't have it on a random face. All right, so what we do is we look at something called the Cauchy stress tetrahedron, which is going to look something like this. So you guys are familiar with the tetrahedron. It has basically 4 faces. All right, so we got 3 in the back and then that 1 on the front. Now, if we were to look at the 3 in the back, those are ones that are aligned with the basis vectors. So it's actually very nice. So if I were to have my tetrahedron here, what I'm going to do is I'm going to analyze all the stresses on the back side of the tetrahedron first. So referring to the first backside, which I have as the nice green surface there, we know that we're going to have sigma 1,1, sigma 1,2, and sigma 1,3. This comes directly from the slide before. Now we're also going to say is that this surface has an area A1. We're going to move along to the other side of the tetrahedron. So again, we're still dealing with the back sides of it right now. And we're going to have the stresses sigma 3,1, sigma 3,2, as well as sigma 3,3. And this is going to have an area A3. Now finally at the bottom, we're going to have the stresses sigma 2,1, sigma 2,3, and sigma 2,2. And it's going to be associated with an area A2. Now these are actually very simple. As we can see, since these surfaces are in the planes formed by the basis sets, it's very easy to determine what those stress components are. So this isn't anything crazy yet. Now what we're going to do is we're going to analyze that front face of the tetrahedron. So the big triangle right there. Now the first thing that we have to do is we have to try and define the triangle. How do we do that? Well, we do that with a normal vector. Remember when I said when I cut something, I can define the angle of the cut with a normal vector. Well, it's the exact same thing I'm doing here, except in 3 dimensions. So we're going to have a normal vector, which is going to be perpendicular to that plane of the frontal surface. So we're going to have n, which is equal to n1 e1 plus n2 e2 plus n3 e3. Now, the second thing we're also going to do is we're going to define the area of this front face as simply AN. All right. And finally, we're going to specify the distance from basically the origin of the coordinate system to this surface as h. And you guys are going to see why we do that a little bit later. Now, the whole key here and the whole reason why we're doing this is because we know that this surface, like every other surface, has a traction vector, Tn. The problem is we don't know the components of Tn. On the other side, since those surfaces were aligned with the basis vectors, we can easily say, oh yeah, it's sigma 1, 1, it's sigma 2, 2, it's sigma 3, 1, etc. We can't do that here because it's not aligned with any of the basis vectors. So this is going to be the goal here. What exactly is Tn for this arbitrary face? Well, the first thing that we're going to do is we're going to split this Tn into components. So we're going to have Tn1, Tn2, as well as Tn3. So these are going to be the components of Tn along those basis vectors. Again, we don't know what they are, but that's what we're going to try and solve for. How do we do that? Well, we do that with Newton's equations of motion. All right, so this is something that you guys definitely know. Basically, the summation of the forces is actually going to be equal to the mass times the acceleration. Nice and simple. You guys are laughing at how easy this is. So if I were to go sum of the forces in the E1 direction, or that horizontal direction, I'm going to have negative sigma 1, 1 times A1. And you guys are saying, hold on, Clayton, hold on. Why are you timesing it by an area? Remember, we're dealing with sum of the forces here. We're not dealing with sum of the stresses. So in order to get my force from that particular stress, I have to multiply it by its corresponding area. So again, sum of the forces in horizontal, I got negative sigma 1, 1 times A1 minus sigma 2, 1 times A2 minus sigma 3, 1 times A3 plus Tn1 times An plus mg, where mg is body forces. Basically, if you have something like gravity, we're going to have to focus on mg. And this is going to be equal to the mass of the particle times the total acceleration of the particle. All right, so this is just summation of forces. And what we're going to do is we're going to repeat this for the E2 direction, so the vertical direction, as well as the E3 direction. So we basically end up with 3 equations of motion, and from these we can start to derive how can we solve for Tn. So again, if we look at this, the whole goal here is we're trying to find Tn, that traction vector on an arbitrary surface. So what we're going to do is we're going to look at the first equation of motion, which we just derived, and we're going to say, all right, I see that I have Tn times An. So what I'm going to do is I'm going to divide all the sides by An. From there, I get something that looks like this. So I cancel out the An when we look at Tn1, but it seems like I just created a mess for myself because I have An basically on every term. Now, what's great about this tetrahedron and why we picked the tetrahedron is that it has a very nice relationship where n times An is equal to A1 E1 plus A2 E2 plus A3 E3. Therefore, Ni is equal to Ai divided by An. You're going to say, hold on, Clayton, I don't remember that. And you're right. I haven't shown you guys this. This is one of those great solid mechanics exam questions. But basically, if we look at the tetrahedron and we look at the basis vectors that make up the tetrahedron, we can actually apply the cross product. And remember the cross product property where I said that if I were to cross 2 vectors, you get the area, the parallelogram, stuff like that. That's where all this comes from. It's very, very ugly to show, but we're just going to use it here. Again, you guys don't need to know the ins and outs of these derivations. So by utilizing this property, and I look at the equation above, well, I see that in my first term I have A1 divided by An. My second term I have A2 divided by An. So therefore I can simplify that equation very nicely by simply going N1, N2, and N3. So these are going to be the components of that normal vector that we're talking about. All right, you're saying, all right, well, it's looking a little bit better, but still a little bit gross. What else can we do? Well, let's focus on this mass term. We have mass term in 2 of the terms. So we know that we can have a nice relationship for mass, where mass is simply the density multiplied by the volume. Now, since we're dealing with the tetrahedron, we know what the volume is going to be. It's going to be An times h, all divided by 3. And this is why we defined that h in the previous slide. So from this, we can substitute the new expression for mass, and we get the following equation. Now, in our current state, we just have a tetrahedron. But when we're proving something, we want to take it smaller and smaller. Think of integration. When we're dealing with the area under the curve, we deal with large rectangles, and then by integration, we decrease the size of those rectangles till they're basically tiny, and that's how we get the exact solution. Well, that's what we're going to do right here. is we have a tetrahedron, but if we want our exact solution, what we need to do is we need to take the limit as the volume of that tetrahedron goes to 0. So what we're going to do is we're going to take the limit of the volume of the tetrahedron, which basically means that we're going to take the limit as h goes to 0. Therefore, those two terms at the end, they go bye-bye, which is perfect for us because now we have an equation, we have it equal to 0, and again, I'm trying to solve for Tn. Therefore, I can solve for Tn, which is equal to sigma 11 n1 plus sigma 21 n2 plus sigma 31 n3. I can repeat this process for the remaining two equations of motion, and I get Tn2 is equal to sigma 12 times n1, sigma 22 times n2, sigma 32 times n3, and then the same thing for Tn3. Now, if we were to look at these equations, Tn1, Tn2, and Tn3, we can see that there's actually a very nice linear homogeneous relationship between the traction vector and the normal vector. And it has to do with that sigma there. And that sigma there is going to be a tensor. All right, this is the whole key here. We look at this and we can say that those three equations there, well, we can basically express them in matrix form. So what we're going to do, just that. So we have Tn1, Tn2, Tn3, those are our traction vector, is equal to some sigma tensor multiplied by our normal vector. And what we're going to do is we're going to simplify this in that our traction vector is simply the transpose of our stress tensor multiplied by n, where sigma here is our Cauchy stress tensor. All right, that's it for the Cauchy stress tensor, nice and easy. So we're going to do some little fun facts. Some of them will be discussed later on right now, and some of them will be discussed later on in the lecture. First of all, this sigma here, it's going to be symmetric. So sigma ij is equal to sigma ji, and this will be proven a little bit later when we talk about mass balance. But it's great for us. Anything symmetric, we're thumbs up, right? Nice and easy. Second thing, there exists a coordinate system which sigma is diagonal. Remember, we talked about diagonalization in linear algebra, and this is going to be important because this allows us to get something called principal stresses, which I'm sure you guys heard of before. Now, we also use this to calculate yield surfaces, and we're going to talk about this when we start talking about material plasticity, stuff like that. But now we're going to go on a simple example, and this will show you guys what exactly a traction vector is. If you guys may be saying, Clayton, I saw the formula, I know how to calculate a traction vector, but what is a traction vector? Well, let's look at our 2D bar, and let's say that I cut this bar in some plane. Now, if I look at this, I can define the cut by that normal vector n. Now again, all the traction vector is just the internal stresses on a surface. So when I cut this, I release those internal forces. In this case, I have a stress vector Tn. All right, and then of course on the opposite side, I have the equal and opposite reactions, blah, 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 blah. Now what we're going to do is we're going to use this traction vector to get some components that you guys are probably a little bit more familiar with. So what I'm going to do is I'm going to expand this out right here and say that I have a traction vector Tn, which is equal to the transpose of our stress tensor multiplied by our normal vector n. And I say, well, one of the things I can do is I can take the projection of this vector onto n. So what I can do is I can create basically this component right there is sigma n. And now this sigma n here, we call this the normal stress. So those of you guys have taken all the way back in undergrad to the mechanics and materials, you guys are familiar with normal stress. This is where it comes from, the traction vector. So this normal stress is the stress component that's going to be perpendicular to our cut, perpendicular to the surface of our cut. How do we calculate it? Well, it's simply the scalar projection of Tn onto n. Now the key here is scalar projection. So when I'm looking at normal stress here, I'm trying to find just a scalar value. I'm not trying to find a vector, just a scalar value. Well, that's perfect because I have a nice formula for that, where sigma n, which is equal to the projection of Tn onto n, is simply going to be Tn dotted with n divided by the norm of n. Now it gets even easier because the norm of n is equal to 1. It's a unit vector. It just describes the direction of the surface. It doesn't represent anything else. So since that's the case, sigma n is just going to be Tn dotted with n. And from there I can find the normal stress on my surface. On the other hand, we can say, well, there's actually a second vector, tau n. Now this tau n, this is called our shear stress. And our shear stress is the stress component that's parallel to that surface. So again, when you guys go back to mechanics and materials, normal stress and shear stress, you guys have heard of those before, I guarantee it. Now you guys know what exactly we're using this traction vector for. It's components like that. So Tn we can see from above is simply the vector addition of the normal stress and the shear stress. So our traction vector is the vector addition. And because we're dealing with vector addition, I don't want to get the symbols confused. So for this particular slide, I'm going to use those little arrows to denote what a vector is. And we know that Tn is basically sigma n, or the vector sigma n, plus the vector tau n. We can rearrange this to create a nice expression for tau n, and therefore we can actually solve for what tau n is. So remember that tau n right now is a vector. So we're going to take Tn, which is a vector, and we have to subtract another vector. Well, we don't have the normal stress vector right now. We have the normal stress magnitude, but we don't have the vector. So in order to get the vector, we take that magnitude, sigma n, and we simply multiply it by n, which is the direction of that vector. And then from there we say, all right, now that I have tau n, and I just want the magnitude of it, or the norm of it, all I need to do is take the norm of it to get my stress component tau n. Now, if I'm looking at the left-hand side, I have a dot product. That means I have a scalar component. All right, so that's going to be very critical. I get a scalar component. On the right-hand side, I'm taking the norm of a vector. Therefore, I get another scalar component. So that's one thing to keep in mind, is when we do these operations, we should get scalar components for both of these. So hopefully by now you guys know exactly what we're using this traction vector for, as well as what exactly is this traction vector. So the last thing that we're going to discuss is going to be principal stresses. So a lot of you guys may have used finite element programs in the past. You guys know that these principal stresses are everywhere in finite element programs. They output things like displacement, strain, stuff like that. However, oh, sorry, I got a question. So you're asking if there should be, in the projection of Tn onto n, there should be the norm of Tn in the denominator. No. And the reason why is we're dealing with a scalar projection in this particular case. We're not dealing with a vector projection. If we were looking at a vector projection, then yes, there would be that in the denominator. Actually, no, there wouldn't be. No, it's because we're dealing with a scalar projection. Yeah, sorry about that. All right, that's all cleared up. All right, so principal stresses. This is, again, something that you guys have seen a lot if you're dealing with finite element programs. And basically, we said that if our tensor is symmetric, there exists a coordinate system lined with eigenvectors, EV, of a stress tensor in which the stress tensor is diagonal. So I called this diagonalization in the last lecture. Basically, what this means is if I have a cube here and I have all these stress components, well, I can actually rotate this cube to the point where there is no shear stress components. All right, if we look at the cube on the right-hand side, there's no more shear. It's all those longitudinal or normal stresses. Now, what is Q? Well, we said that Q is actually going to be a rotation matrix consisting of the eigenvalues of the stress tensor. So the first row is going to be the first eigenvector, the second row is going to be the second eigenvector, and the third row is going to be the third eigenvector. What does this mean mathematically? Well, let's say that I have my state of stress defined by the Cauchy stress tensor, and I were to diagonalize it with that particular coordinate transformation matrix, then my sigma prime is simply going to be a diagonal matrix full of zeros, and the diagonal components, which I call sigma 1, sigma 2, sigma 3, well, those are going to be the eigenvalues. All right. Now, if we look at this, depending on which row of our coordinate transformation matrix Q we make a particular eigenvector, it's going to be all over the place. So what we typically do, just to keep some sort of consistency, is we say that sigma 1 is greater than sigma 2, which is greater than sigma 3. So when you guys find the three eigenvectors and you guys want to express it as a diagonal matrix, we usually put the largest component in the 1, 1 spot, the second largest component in the 2, 2 spot, and then the smallest component in the 3, 3 spot. So hopefully that makes sense to you guys. But that's basically it for the Cauchy stress tensor. Is there any question about that? It's a bit longer. Hopefully doing so good so far. I know that this lecture is a lot to take in. It's basically compressing one whole semester of solid mechanics down your throat in one lecture, but I think that you guys are doing fine so far. At least I hope so. I can never tell. But with this being said, let's take a break. Let's take let's say a 5-minute break. No, more than that. We'll go 8-minute break. I might need those extra 2 minutes. So let's take an 8-minute break. We'll come back at 9:08, and I'll be right here in case you guys have any questions. And then from there, we'll continue on. All right, guys, welcome back. Oh, let's continue on. I I'm gonna apologize again. Yeah, the first part of solid mechanics is always a lot to take in. It's again, I crammed probably half a semester down your throat in 1 hour. Now it's time for the second half of the semester. All right, so I'm going to keep this short and sweet. I want to get into the actual thing today, which is Euler-Bernoulli beams. I want to show you guys what the lectures are supposed to be like rather than just being a snooze fest through the theory. All right, so we're going to talk about stress measures right now and get into constitutive laws. That's going to be the goal for right now. And then after that, we're going to discuss the actual assignment and Euler-Bernoulli beams in general. So hopefully we can make it nice and easy. So uh, the hard part's over. Let's keep it to the good part now. All right, so we're going to start with stress measures. And this is why exactly, or what exactly can we do with that Cauchy stress tensor that we defined before. All right, so let's get this going. So the first thing that we can calculate is the hydrostatic stress tensor. So the hydrostatic stress, which I'm going to call P, is a scalar representing the average normal stress on the faces of the infinitesimal cube. So if I have a cube and I have my stress tensor, the stresses the cube is subjected to, then my hydrostatic stress P is simply going to be the average of those diagonal components. So it's going to be sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3. Now, we're taking the average of them. So of course, after we add them all together, we simply divide by 3. Now you guys look at this and you say, hold on one second, I thought that from linear algebra, if we're taking the sum of a tensor, some of the diagonal components of a tensor or matrix, well, that's actually the trace. And you're completely correct. So the hydrostatic stress P, it can be calculated as the trace of sigma divided by 3. And please don't forget to be divide by 3. Me personally, I'm so used to taking the trace for the hydrostatic stress that a lot of the times I forget to divide by 3. You got to keep in mind that it's the average stress and not just simply the trace. Now, one thing that's nice about this is that trace there, we know that that's actually invariant. Therefore, it remains constant no matter what basis set is selected. Now, this is great for us because we can calculate it from either the non-diagonal stress tensor, so that'd be the stress tensor that we see above, or we can calculate it from the diagonal or the principal stress tensor. The answer is going to be the exact same. Now, our hydrostatic stress tensor can be defined as follows, where we're simply going to take that hydrostatic stress P and multiply it by the identity matrix to get basically a diagonal matrix full of zeros, with the diagonal components simply being equal to P. Hydrostatic stress tensor, piece of cake. The second one, which sounds really scary, deviatoric stress tensor. It sounds like a Halloween costume or something like that. It's actually very, very nice, even though it sounds like complete garbage. The deviatoric stress tensor, which we call S, is obtained by subtracting the hydrostatic stress tensor from the stress tensor itself. So S right here is simply going to be sigma minus P times I. Remember that Pi, that's the hydrostatic stress tensor. So we can expand it out. We have our stress tensor minus our hydrostatic stress tensor. And we get that S is simply going to be our stress tensor. The only difference is that we're going to subtract the hydrostatic stress from each of those diagonal components. Now, because we incorporated that hydrostatic stress, there's actually a very nice property with this deviatoric stress tensor, and that the trace of it, or the sum of the diagonal components, is actually going to be equal to 0. So you guys are saying, all right, Clayton, you showed us two different tensors, hydrostatic, deviatoric, but why? Why are you doing this? Are you just doing this to bore me? Well, I'm not. They actually have purposes. So the hydrostatic stress tensor is actually responsible for changing the volume of a body. And if we look at that stress tensor, it's a diagonal tensor full of P. We can actually see it, I guess, right here. I'm not sure if you guys can see my mouse, but this is the hydrostatic stress tensor there. And remember that when we were talking about uniform extension and contraction, this is the matrix that we had to describe it. We had the K1, K2, and K3, and we saw that depending on what our value of K is, it either expands or contracts. So that's the hydrostatic stress tensor. The deviatoric stress tensor is responsible for changing the shape of the material while keeping the volume constant, or shearing the material. Now, as you guys are going to see later on when we start talking about plasticity, this deviatoric stress tensor, it's going to be one of the most important stress tensors out there, really. All right. So we're going to talk now about von Mises stress. So before we were talking about two different stress tensors, but now when we're talking about von Mises stress, we're actually going to talk about just a scalar value. The reason why? Well, let's think of this. Let's say that I'm interested in knowing the response of this potato. All right, so what I do is I take this potato to the structural lab and I subject it to some uniaxial tension. From there, I can get a nice stress strain curve that looks something like this. All right, so nothing too special. But then I say, well, hold on 1 second. There's a very unique point here where that behavior actually changes. Now, even though I'm talking about a potato, you guys can probably see that I'm talking about steel right now. And this is commonly referred to as the yield point. There's a point on the stress strain curve in which the steel changes behavior, or we say that it yields. Now, if we were to look at this and say, well, if I measure my yield stress as, let's say, 400 MPa, and I were to put some steel in tension to value 500 MPa, and I were to say if the yield stress is 400 MPa, and I were to subject it to 500 MPa, does it yield? Well, you're saying, well, of course, Clayton, you're an idiot. Of course it's going to yield. 500 is greater than 400. Or vice versa. If I subject it to 300 MPa, will it yield? Well, no, Clayton. It's less than the yield strength. No problem. So in a uniaxial case, it's very simple to determine when a material yields or if it doesn't yield. However, if I take that same potato and I were subjected to a triaxial state of stress, so I have shear stresses, I have my normal stresses, all of those stresses, does it yield? Well, it's actually very difficult to tell. So the moral of the story here, very easy to determine when the material will yield or change behavior in a uniaxial case. However, it's not so easy in a Cauchy state of stress or a 3D stress state. So one of the things that we're going to do is we're going to introduce something called the von Mises stress measure, which basically takes our 3D stress state. I don't know why I can't say that very well, but it basically converts it to an equivalent uniaxial stress state. And since we have an equivalent uniaxial stress state, we can then very easily determine if something yields or if it doesn't yield. So how do we do that? Well, we go into a nice formula. So the von Mises stress is actually a function of the second invariant of the deviatoric stress tensor. Remember that the first invariant is a trace, which we've seen up here. The third invariant is the determinant, which you guys will see pop up everywhere once we start getting into finite element. And we said that second one is kind of weird. We don't really know what we do with that second invariant. Well, this is exactly what we do. We use it to determine the von Mises stress. So the von Mises stress, which is a scalar, is going to be equal to the square root of -3 multiplied by the second invariant of the deviatoric stress tensor. Remember, this is the deviatoric stress tensor, not the actual stress tensor. So we say, all right, well, I actually know what that second invariant is. It's 1/2 of the trace of the first invariant, or I guess the first invariant is the trace. It's 1/2 of the first invariant of S minus the first invariant of SS. Now remember that when we define this deviatoric stress tensor, we said it has a very nice property in that the first invariant, or the trace of S, was actually equal to 0. So therefore, we know that that component's going to be equal to 0. We can simplify this to 3/2 of the first invariant of SS. We can then expand this into a component form, and we can basically conclude that this looks disgusting. Nothing too crazy about it. So what we're going to do is we're going to take that definition, and we're actually going to simplify it in terms of the Cauchy stress components. So sigma 1, 2, sigma 1, 3, rather than the deviatoric. It just makes our lives a little bit easier. So what we do is we get this nice long equation here where our von Mises stress is actually sigma 1, 1 minus sigma 2, 2 squared plus sigma 2, 2 minus sigma 3, 3 squared plus sigma 1 minus sigma 3, 3 squared plus 6 times sigma 1, 2 squared plus sigma 1, 3 squared plus sigma 2, 3 squared, all divided by 2 and then square rooted. So even though I said that we made it look nicer or simplified it, it doesn't look very simplified. But as you guys will see in a lot of the scenarios that we deal with in real life, many of the stress components are actually equal to 0. So this right here, this is the most general form of the equation. But once you guys start getting, let's say the shear stress is equal to 0, it starts simplifying quite nicely. Now this is great because we can calculate a value or a von Mises stress value based on our 3D stress state, and then we can compare it to our yield stress. So again, let's say that our potato yields at 400 MPa, but we subjected it to a 3D stress. Well, all we need to do is input the components of our 3D stress into this equation. We get a value of von Mises stress, and then all we have to do is compare the von Mises stress to our yield stress to determine if yielding has occurred or not. All right, so it makes it really, really easy in that sense. Now, the last stress measure we're going to talk about is something we call the maximum shear stress, or some of you guys may have referred to this as the Tresca yield criterion. So if you guys hear Tresca, it's basically going to be the exact same as this. So another stress measure is the maximum shear stress. How do we calculate it? Well, it's actually very, very nice, where the maximum shear stress is going to be the maximum of the difference between all the principal stresses divided by 2. All right, so the key here that I really want to hammer in is that these right here, those stress components, those are the principal stresses. So if we look at this formula, we say, oh, it's really easy. But now we realize, oh, it may not be so easy. The reason why, those are principal stresses. So if we're given a 3D state of stress, we can't just use those particular values. What we actually have to do is diagonalize the matrix first, and then we can input our values. So if we look at this equation, we can see that the maximum shear stress is equal to half the maximum difference between the principal stresses. So my question is going to be, why? Sorry, I need a quick water break. All right. The reason why is because of this. If we were to think of a diagonal matrix, so in our diagonal matrix, those are the principal stresses. The key here is they have no shear stresses, because again, it's a diagonal matrix. Now, if I were to take this matrix and rotate it 45 degrees, we can see that we now have shear stresses, all right? Then if I were to take this again, rotate it 45 more degrees, well, then I'm back into my principal stresses. So the key here is that when we rotate the matrix from the principal coordinate system, we start to develop shear stresses, but as we keep rotating it, then we just end up back in the principal coordinate system. So we know that the maximum shear stress is going to happen somewhere in between 0 and 90 degrees of rotation. Now, I've already hinted that the maximum is going to occur at 45 degrees, all right? So when we rotate the principal coordinate system by 45 degrees, that's when we get the maximum shear stress. But again, you guys might be asking, well, why? Why is this the case? So what we're going to do is we're going to figure out why this angle causes the maximum shear stress. So let's say that we have a principal stress tensor of sigma 1 and sigma 2. Again, we're going to apply a counterclockwise rotation matrix, cosine of theta, sine theta, negative sine theta, and cosine of theta. But instead of putting in values of theta, we're just going to keep it general, all right? So if I were to transform this matrix, so sigma prime is equal to q sigma times the transpose of q, I get the following expression. Now remember that we are interested in the shear stress right here. We want to make sure that this value right here is a maximum. So what we're going to do, how do we get a maximum? Well, all we need to do is take the derivative, set it equal to 0, and then solve. And it's actually that simple. So what we're going to do is now that we have an equation for shear stress, we're going to take the derivative of it with respect to theta and set it equal to 0. So I have one equation with one unknown. I get that cosine squared of theta is equal to sine squared of theta. Therefore, if I'm only interested in the domain between 0 and 90 degrees, my only solution is going to be 45 degrees. I take that 45 degrees, I substitute it into my equation, and I get that sigma 1, 2, or the maximum shear stress for component sigma 1, 2 is equal to sigma 2 minus sigma 1 sine 45 times cosine 45. Therefore, I get that the maximum shear stress is half of the difference between the two principal stresses. So hopefully that makes sense to you guys. And we can repeat this for sigma 1, 3 as well as sigma 2, 3. All right. And that's it for stress measures. It's more or less a little bit of an introduction. Once we start talking about the finite element method, we're going to start talking about more of how we calculate stresses, how we calculate strains, stuff like that. So it's just a little bit of an introduction into some stress measures. It shouldn't be too bad at all. You guys doing good? Hopefully. So next thing, I'm going to breeze through. So this is something that I have, of course, videos you guys have probably seen that for each of the topics I've been posting YouTube videos. So I will have a nice video for this if you guys are very interested, but we're going to breeze through this. We don't really need it too much for today, and the solution is kind of trivial, so it's nothing too outstanding. So we're going to talk about balance equations, and these allow us to basically get two things. I'm just going to go through it. Balance of linear momentum and balance of angular momentum. All right, so this is the whole goal of balance equations. Again, I will do a slow video where I discuss each of these in depth if you guys want to know more. But basically, when we look at balance equations, we talk about these two things. Now, these two things are actually very important because the first one, balance of linear momentum, that establishes equilibrium for our 3D stress state. And the second one, balance of angular momentum, that is actually what we use to prove the symmetry of the Cauchy stress tensor. All right, so that's kind of the goal here. Again, I'm just going to fly by. Nothing too crazy because I'm going to talk about the actual fun stuff. Balance of linear momentum. So you guys have the notes, so you guys have the proof if you guys want. But basically, you guys end up with, keep going, equations of equilibrium. So basically, this is what the balance of linear momentum ends up with, 3 equations of equilibrium. And we will use these later, but again, it's not very important right now, so that's why we're just flying through it. The second one that we have, balance of angular momentum, and the whole goal of balance of angular momentum is to basically prove that our stress tensor, sigma, is symmetric. And now it's pretty gross derivation, but it's pretty easy at the end. So again, just flying by this, sigma ij is equal to sigma ji. All right, nice and fun. So now we're going to talk about the actual fun stuff today. Constitutive laws. So we have 2 sections left, constitutive laws and Euler-Bernoulli beams. Now again, your assignment is going to be Euler-Bernoulli beams, which is why I want to take more time focusing on that so that when you guys get to the assignment, you guys go, oh, Clayton, this is easy. I know exactly how to do this. That's my personal goal, at least. But before we do that, we have to talk about constitutive laws, which is basically stress, strain. I keep saying stain, which makes no sense at all, but a stress-strain relationship. So remember that at the beginning of the lecture, we talked about our strain tensor. We talked about our stress tensor. Now what we're going to do is we're going to find a relationship between both of them, which makes complete sense to me. So at least hopefully it makes sense to you. If we think about finite element, and if you guys think back to 660, I know not all of you guys have taken 660, but basically in 660, you guys did the finite element method. You guys put a bunch of nodes on things and you guys solved for displacements. All right, but that's where you guys kind of ended things. You solved for those displacements. You said that my displacements are, let's say, 6 meters, and you guys are happy. Now, what we've established with the strain matrix is once we know displacements, we can calculate strains, which is great. Now, we can take that a step further and say, well, if I know strains, can I calculate the stresses? Well, the answer is actually going to be yes. So that's going to be the whole goal of what we're going to talk about right now is if I know the strains, can I find the stresses? Or if I know the stresses, can I find the strains? All right. So the goal is how can I transform between a 3-dimensional matrix and another 3-dimensional matrix? Well, a linear map between M3 and M3 is actually a 4th order tensor. Now, when I was talking about tensors, and I said that there's only one section in this course in which the difference between a matrix and a tensor is going to be important, it's going to be this particular part. All right, so I'm going to try and keep it in matrix talk most of the time so you guys can see what exactly is going on. But as you guys are going to see, there's going to be one section in which will make no sense at all, but because in that particular section, we're talking about tensors. All right, so let's say that I want to find a value sigma 11 based upon our strain tensor. All right, so what I can do is I can say sigma 11 is going to be some constant times epsilon 11 plus some constant times epsilon 22 plus some constant times epsilon 33, etc., etc., etc. So if we look right here, our one component of our stress tensor takes 9 components of our strain tensor. So if I were to represent this in matrix form, it's going to look pretty ugly. Inputting this equation, it actually crashed PowerPoint and I had to restart. It was not fun at all. So right now, we have a big, disgusting matrix. Now, if I have stress on one side and I have strain on the other side, and question for the chat, what is going to be the unit value of this matrix, C? The C matrix above. Is it going to be an MPa? Is it going to be in newtons? What do you guys think? If I'm converting from stress to strain. All right, you guys are all saying MPa. You guys are exactly correct. It'll have units of MPa. And because of such, we call C the stiffness matrix. Now, for those of you taking 660, you guys are going to say, hold on, Clayton, what are you talking about? The stiffness matrix has different units. Well, they're actually the exact same thing if you think about it. So C right here is actually our stiffness matrix, and it converts stresses, or sorry, we're able to obtain stresses if we know the strains. Now, if we look at this and take a step back, we can see the matrix is 9 by 9. So it has 81 constants. Really gross. No one wants to deal with 81 constants. So the whole goal of constitutive laws, how can we take this most general form and simplify it? Well, the first thing that we can do is we can realize, well, hold on a second. In the previous one here, I have components sigma 2, 1, sigma 3, 1, sigma 3, 2. But wait, we said that that stress tensor is actually symmetric. Therefore, sigma ij is equal to sigma ji. So instead of having 9 components of stress and 9 components of strain, well, we actually only have 6. Therefore, we can start simplifying this matrix. The first one is saying, well, if my stress tensor is symmetric, therefore ij is equal to ji, well, that must hold true for the stiffness matrix as well. And the same thing for the strain tensor. KL must be equal to LK. Therefore, I can simplify it down into a 6 by 6 matrix rather than a 9 by 9. Because again, I don't need to know the stress components sigma 2, 1, sigma 3, 1, and sigma 3, 2, because they're exactly the same as sigma 1, 2, sigma 1, 3, sigma 2, 3. So just right here, we're good to go. We reduced it from 81 constants all the way down to 36. So we're looking pretty good right now. Now, one thing that I want to note, and this is something that gets the undergrads every single time. I love it, but it's kind of an evil trick. We realize that the symmetry of the stress and the strain tensor does not result in the symmetry of the stiffness matrix. So one of the questions, as you guys are going to see, the stiffness matrix here is going to be symmetric. And now what you say to the undergrads is you say, well, why is it symmetric? And they always go, well, if the strain tensor and the stress tensor are symmetric, that's why this is symmetric. But if we look at the stiffness matrix right now, it's not symmetric right now. We just reduced it from 81 to 36 coefficients. So the symmetry of the stress and the strain tensor, it does not lead to the symmetry of the stiffness matrix. How do we obtain the symmetry of the stiffness matrix? We look at preservation of energy. This preservation of energy is how we obtain the symmetry of the matrix. All right, so further reductions can be made if the material is elastic, which means it preserves energy. So when I take something, take a bar of steel, and I load it, it stores energy. Now, when I unload it and put it back to its original position, all of that energy is fully recoverable. All right, and that's what we're going to use to prove this symmetry of the matrix. So what we're going to do is we say, all right, well, if I were to take a material and load it, all right, that's all I'm doing, taking material and loading it, the stored energy is simply the area under that curve. So that stored energy, which I have as U bar, that's the stored energy once I load the material. Now, of course, once I unload the material, it follows the same path. The area under the curve is going to go back to 0. That's what I mean by it's fully recoverable. Now, if I were to look at this and say, well, if it's the area under the curve, and the curve is just a triangle, my stored energy is simply 1/2 of sigma times epsilon. Nice and easy.
I found this on the web.
Ooh, what was that? my watch. And from there, we can say, well, hold on a second. In a uniaxial case, because of Hooke's law, we know that the stress there is actually just going to be our stiffness matrix multiplied by epsilon. And from there, we get that this energy is actually equal to 1/2 of our stiffness matrix multiplied by epsilon squared. Now, keep in mind that right now we're doing a uniaxial case, a 1D case. So that stiffness matrix C, that's equivalent to the Young's modulus right now. And you guys know what the Young's modulus is, but we'll discuss it more later. So what I'm going to do is I'm going to take the partial derivative now of this energy function with respect to epsilon. It's just the partial derivative of 1/2 of C times epsilon squared. Well, simple, just bring the 2 down from the epsilon. I end up with C times E. Now remember that this C times E, well, that's just actually equal to sigma. Therefore, this derivative of the partial energy, the partial derivative of the energy with respect to epsilon is going to be equal to sigma. Therefore, sigma ij is going to be the partial U divided by partial epsilon ij. All right, and this is going to be the key to proving the symmetry. Because what we're going to do is we're going to say, well, if this is a nice linear relationship, then our constant Cijk is going to be the partial derivative of sigma ij with respect to epsilon kl. Now we're going to take that that sigma ij, and we say, well, that's actually equal to the partial derivative of the energy with respect to epsilon ij. Therefore, I get this nice equation over here, where Cijk L is equal to the second partial derivative of U with respect to epsilon ij, and then with respect to epsilon kl. Now here's the key, right here. Doesn't matter which order I take these in. If I differentiate with respect to epsilon ij first and then to kl, well, that's going to be the exact same as if I take it with respect to kl first and then with ij second, because this is a nice simple function. There's no discontinuities, anything like that. Therefore, I can actually swap it around there, and we know that this is going to be equal to CKL ij. Therefore,Cijkl is equal to CKL ij. Therefore, our stiffness matrix C is actually symmetric. Now, again, I really want to emphasize this because I don't want to scare students. We're not dealing with derivations in this course. We'll deal with derivations in the finite element aspect, but for these, all you guys need to take from this slide is that the stiffness matrix is symmetric. If you guys are able to do that, then I'm happy. All right? So that's the second reduction. Utilizing this symmetry, we know that we can reduce the number of independent constants from 36 to 21. We're saying, well, hold on, Clayton. How'd you do that? Well, remember that this is symmetric. So for instance, C1122 is going to be equal to C2211. Therefore, all of those red constants, we already know them because they are actually defined above. And this is a result of elasticity. So you're saying, well, we're at 21 constants right now. I don't want to measure 21 constants. No one wants to measure 21 constants. So how can we reduce this even further? Well, to do that, we are going to use planes of symmetry. All right, and we're going to look at three specific materials which each have their own planes of symmetry. The first one is an orthotropic material. The second one is transversely isotropic. And finally, the third one is just simply isotropic. And isotropic is the one that we're going to be used in all of our finite element proofs, stuff like that, which is great because isotropic, a little bit of a spoiler alert, we're able to get those 21 constants all the way down to 2. Just 2 constants, and that's it, which is perfect for us. All right, so before we talk about that, what is a plane of symmetry? Well, if the constant law governing a material remains the same after a reflection about a plane, that plane is referred to as a plane of symmetry. Now, it's kind of hard to picture what exactly that means. So let's say that we have a plate and we have 2 directions defined, E1 and E2. Well, we know that sigma ij is equal to Cijkl times epsilon kl. Now, if I were to say that this vertical plane here was a plane of symmetry, that means that this plate would behave the exact same way if that E1 direction was actually flipped or reflected. Therefore, if I were to transform this by a matrix Q, which is -1, 0, 0, and then 1, so just flipping that E1 axis, what I'm basically saying is that this behavior is going to be the exact same. So that sigma prime ij, which is equal to C prime ijkl times epsilon prime kl, it's going to be the exact same. So if sigma ijkl is the same as sigma prime ijkl, then we say that that plane there would actually be a plane of symmetry. And this is what's going to help us drastically reduce the number of coefficients. Now, each material, as I said, it has different planes of symmetry, and that's what we're going to look at specifically. The first one is an orthotropic linear elastic material. And this orthotropic material has basically 3 planes of symmetry with unit normal planes aligned with the basis vectors. This basically means that if I have basis vectors E1, E2, and E3, so 3 directions, if I were to stretch the material in E1, it's going to be different than if I stretch the material in E2, which is going to be different if I stretch the material in E3. So each direction is going to behave differently for an orthotropic material. So basically the behavior is different along the 3 basis vectors. Now, if the behavior is different for all 3 basis vectors, this is going to be our more complex case. All right. However, since we know that the behavior is going to be each plane is a plane of symmetry, the constitutive law must be the same after the following transformations. So basically, if I were to transform the E1 axis, the E2 axis, or the E3 axis, the behavior should be the same. Now, the question is, how do I transform? Because remember, right now, our constitutive law is a 6x6 matrix, 6x6. And these reflection matrices are 3x3. How do I rotate them? Well, this is the only part of the course where we have to realize that even though we express our constitutive law as a 6x6 matrix, it's actually a 4th order tensor. It's not a 6x6 matrix. So if I were to transform it, I basically go to this equation over here, where C prime ijkl is equal to QMI, QNJ, QRK, QSL times CMNRS. Even I can't even say that. But this is a transformation of a 4th order tensor. So again, this is why we have to kind of distinguish sometimes that we have a 4th order tensor and not really a matrix. Now, this looks confusing at first, but there's actually a summation over MNRS from I equals 1 to 3. So it gets even more complex. All right, so again, in this class, thumbs up. We don't need to know derivations. It's good to go. So what I'm going to do is I'm going to show you what exactly this results in. So from this equation here, we can relate C prime to C. And from there, we can actually start canceling out a lot of components. More specifically, for an orthotropic material, this results in 12 of those 21 components being actually equal to 0. So we see that we've now really simplified our stiffness matrix. And what this specifically did is it decoupled the shear. What do you mean by that, Clayton? Well, if I were to look at the components, sigma 1, 1. If I were to calculate that, now I have three components here. And what I can see is that if I were to calculate sigma 1, 1, we can see that those three components respond to epsilon 1, 1, epsilon 2, 2, and epsilon 3, 3, meaning that my normal stresses are not related to my shear strains and vice versa. All right, so if I'm calculating my normal stresses, which are the 1, 1, 2, 2, and 3, 3, then I'm only relating to the normal strains 1, 1, 2, 2, 2, 3. The shear strains are independent of the normal stresses. That's what we get for that first shear decoupling. The second one, which we can see down here, is that each shear stress is only related to the shear strain in the exact plane. For instance, my sigma 1, 2, that's only related to epsilon 1, 2. My sigma 1, 3, that's only related to my epsilon 1, 3. So this is what I mean by shear decoupling. All right, so it's great. A lot of zeros for us. More zeros, the better. Now, for an orthotropic linear elastic material, we can actually fill in all of those coefficients with engineering coefficients. So therefore, I can actually express this matrix C as follows. So if we look in here, we actually have 9 different components. The first one is the Young's modulus, which is big E, capital E, II, and this is the ratio of uniaxial stress to uniaxial strain in the direction of the basis vector EI. So if I were to look inside this matrix here, I see that I have E11, E22, and E33, which makes sense because remember that we said that the behavior along each of the different basis vectors is all going to be different. And because of that, we have 3 different values of Young's modulus, depending in which direction you want to measure it. The second one that we have is the Poisson's ratio, which is nu ij, and this is the negative of the ratio between the axial strain in the direction ej to the axial strain in the direction ei when the material is uniaxially stretched in the direction of ei. So it's a lot to take in, but in essence, you guys already know what Poisson's ratio is. It's something that's very common in engineering. Basically, if I were to squish something, we would expect. Now, I'm saying expect because there are cases where the opposite is true, but if I were to squish something, it expands. That's the effect of Poisson's ratio. All right. And finally, last one that we see kind of down there in the bottom right corner is the shear modulus Gij, which is the ratio of shear stress sigma ij to the engineering shear strain, which is gamma ij, which is equal to 2 times epsilon ij in the plane defined by ei as well as ej. So for each one of these coefficients, and I look in my matrix, I can see that I have 3 of each. I have 3 different Young modulus, 3 different Poisson's ratio, and 3 different shear moduli. All right? But we have to realize a couple facts. The first one is, when I did my original matrix, I had stress times C times strain. Basically, I had the stiffness matrix, right? If I were to look at this matrix right here, I flipped it. Instead of having stress on the left-hand side, I now have strain on the right-hand side, and I have stress on the right-hand side. So when we flip it like that, this is actually called the compliance matrix. So this is expressed as strain is equal to something times stress, which is the opposite of the stiffness matrix. So if I have my stiffness matrix, all I need to do is invert it to get the compliance matrix. Or vice versa. If I have my compliance matrix here, which is D, all I need to do is invert it to get my stiffness matrix. Now, one of the things that we also said is we know that for any sort of stiffness matrix or compliance matrix, it's symmetric. Therefore, in this case, we know the components. Therefore, the Poisson ratio ij over EII is actually going to be equal to the Poisson's ratio ji divided by EJJ. All right? So if we look up here, we can see that we have 2 components. If I were to look at the top row, I have the Poisson ratio 2, 1 divided by E22. Now on the other side, I have the Poisson's ratio 1, 2 divided by E11. So even though the components are completely different, we know that the value of them must be the same because of the symmetry. So it makes our lives a little bit easier. Now, what's going to make your guys' lives a lot easier is that we don't really deal with orthotropic materials too often, at least for civil applications. One application of an orthotropic material would be wood. As you guys know, wood has different fibers, and depending on which direction we load those fibers, it's going to make a difference. Think about chopping wood. We know that there is a very special way of chopping wood. You always want to go down with the fibers. If you guys are going the other way, well, you're going to have a hard time. That would be an example of an orthotropic material. However, like I said, we don't deal with them very much, so it's kind of good for us. The next one is a transversely isotropic linear elastic material. Now, for a transversely isotropic linear elastic material, there exists a plane in which every plane perpendicular to that plane is a plane of symmetry. What does this mean? Well, basically means that the behavior is the same in two directions. Basically, if I were to stretch it along E1, well, that'll be the exact same as E3, but if I were to do E2, then E2 would be different. An example of this is typically soil layers. If we look at soil layers and I were to stretch this along E1, well, that's going to be the same as E3. However, if I were to stretch it vertically, we know that that response is going to be different. Therefore, we know that we actually have infinite amount of planes of symmetry as long as these planes are vertical. And because of that, we can also say that we have basically an axis of isotropy right there. All right. So again, the key takeaway here is that it's going to behave the same along two of the basis vectors. And from here, we can actually simplify our compliance matrix to as follows. So we went from 9 coefficients in the orthotropic case down to 5, which is great. But again, remember that this material is symmetric. Therefore, we have a nice relationship which can be expressed as follows. So transversely isotropic materials, again, I said it's more soil. And I know that there's some geotech kids here. Yeah, it's dirt, basically. But yeah, we won't talk about them too much in our more or less our civil applications, even though geotechnical is a great civil application. We're talking more about beams, stuff like that. So if we're talking about beams, probably the most common thing you guys can think of is steel. What is steel? Well, steel is an isotropic linear elastic material, which means that the behavior or the response of it is going to be the same in any direction. If I were to stretch it along E1, that's going to be the same as E3, which is going to be the same as E2. All right, which is perfect. It's independent of the coordinate system. And because of this, we get the nice relationship above. And as we can see, we went down to just two material constants. First one is the Young's modulus, which of course, in this case, is going to be the slope of the stress strain curve during a uniaxial tension test. And then our second one is the Poisson's ratio nu, which is negative the ratio of the transverse strain to uniaxial strain during a uniaxial tension test. Nice and easy. Now, you guys looking at this, and I say, well, I see nu, I see E, but I also see G. So you guys may be saying, Clayton, you just said we reduced it to two coefficients, but we have a third one, G. Well, what exactly is G? Well, G is called the shear modulus, and the shear modulus is the slope of the shear stress versus the engineering strain of a linear elastic material. Now, I know that that means nothing to you guys right now, but what it basically means is this. G is equal to E divided by 2 multiplied by 1 plus nu. So even though it appears as a separate coefficient in our compliance matrix, it's actually just a function of E and V. So if we know E and V, we can calculate G, we're good to go. Hence, for an isotropic material, we only have those two constants. The second one is called the bulk modulus K, which is basically the shear modulus, the bulk modulus, not the shear modulus, is the slope of the hydrostatic stress versus the volumetric strain of a linear elastic material. It can be calculated as K, which is equal to E divided by 3 multiplied by 1 minus 2 times nu. And this is basically an indication of how resistant a material is to compression. So in this particular course, you guys won't see the bulk modulus very much. I'm going to be honest with you guys. What you guys will see moving forward a lot are these two conditions. The first one is the plane stress condition. If you guys ever modeled something in finite element in 2D, you guys are either using plane stress or plane strain, or maybe axisymmetric, but we'll talk about that one way later on. So the first one is a plane stress condition, and this is assumed when all the stresses on the material act on the same plane. Therefore, sigma 1,3 is equal to sigma 2,3, which is equal to sigma 3,3, which is going to be equal to 0. Therefore, my stress tensor is going to look like this. Nice and easy, right? And then from there, we can calculate our strain tensor, and we can see that the shear strains in the 1,3 and 2,3 directions are going to be equal to 0. Now, because of this, we can actually create a much simpler constitutive law if we have a plane stress condition, where we can calculate epsilon 1,1, epsilon 2,2, and epsilon 1,3 simply by using the very shortened compliance matrix multiplied by sigma 1,1, sigma 2,2, sigma 1,2. Now, if you guys are thinking, oh, well, this isn't too bad at all, we have to keep in mind that this particular compliance matrix does not calculate epsilon 3,3, which we have up there. Epsilon 3,3 is not equal to 0. Sigma 3,3 is equal to 0, but not epsilon 3,3. It's part of the assumption. So to calculate epsilon 3,3, we utilize the assumption that the material can expand or contract freely in the E3 direction. Now you guys say, what exactly implications does this mean? Well, this is kind of the whole key of plane stress. If a material can expand or contract freely in that third direction, it usually means that something's very thin compared to its length. So a good example of this would be a steel plate. If I have a big giant steel plate, but it's only, let's say, 10 millimeters thick, a plane stress condition would be perfect for the steel plate. Now, we have a second condition called plane strain. Now, in this case, this is assumed when all the strains on a material act in the same plane. So before all the stresses acted on the same plane, well, now we're talking about all the strains acting on the same plane. Therefore, epsilon 1,3 is equal to epsilon 2,3, which is equal to epsilon 3,3, and that's all going to be equal to 0. Therefore, we have our strain tensor, a bunch of zeros, and we can calculate our stress tensor. All right, so because of this, since we have all this nice simplification, we can create a nice simple constitutive law between the two. But just like before, remember that this does not calculate sigma 3,3. All right, so we're going to have a separate calculation for sigma 3,3, which is under the plane strain condition. It's typically assumed when a material is restrained from expanding in that third direction. So remember, plane stress, it can freely expand. Plane strain, it can't expand. All right, so we're limiting that. And in this case, our sigma 3,3 is going to be our Poisson's ratio nu multiplied by sigma 1,1 plus sigma 2,2. So nice and easy. All right, and with that, we are done constitutive laws. So we're going to take a break and we're going to get into Euler-Bernoulli beams. Now, this is going to be important. It's very easy, but it's very important because this is where your first assignment comes in. All of this right here, Euler-Bernoulli beams. So we're going to cover the lecture. It shouldn't take us too long, but then what we'll do is we'll get into a detailed example so that you guys know exactly how to solve your guys' assignment for the week. So what we'll do is we'll take a 10-minute break. I know you guys could probably use a stretch and well, maybe wake yourselves up. I know that we just covered a lot of theory, but hopefully you guys are doing fine. So again, we'll take a 10-minute break. We'll come back at 10 o'clock. We'll discuss Euler-Bernoulli beams as well as the assignment, and you guys should be good to go for the week. Now, I also want to mention that up until this point, we haven't covered any finite element yet. So don't worry, that'll start happening next lecture. The goal of this lecture will be very clear at the end of this particular section. I promise you. So if you guys want to see that big fireworks finale, just wait until the end of this, and you guys will be, oh, that's why we're learning solid mechanics. Okay, that makes sense. All right, guys, so again, 10-minute break. I will see you guys at 10 o'clock. Get yourself something nice to eat, maybe do a stretch, use the washroom, stuff like that. All right, guys, see you at 10. All right, guys, welcome back. So this is going to be the last part of the lecture. It's going to be the fun part of the lecture, because this is when the course really starts. Up until this point, we reviewed linear algebra, boring. Reviewed solid mechanics, not boring, but a lot to take in. Now we're going to get into the actual course. Now, when we're dealing with finite element method, what we're basically doing is we're finding approximation methods. Now, one of the most common things that we want to try and approximate, of course, is going to be displacements, stresses, and strains, everything that we talked about. So what we're going to do in this particular segment of the lecture, I guess, is we're going to talk about what if we want an exact solution. Again, finite element method, it's all about approximating. But what if we want an exact solution? And that's going to be very key here, because what we're going to do is we're going to discuss an exact solution. We're going to discuss basically two things. One is all the simplifications and assumptions that we need to make this work. And then the second one is what exactly we need to do to solve the exact solution. All right, so we're going to discuss Euler-Bernoulli beams. Let me just click this so we're good to go. All right, so Euler-Bernoulli beams are actually very simple. So beams are a very common topic in engineering. Even though I know that I have some chemical engineers in here, some mechanical engineers that are not civil, basically, I know that you guys have all dealt with beams before. That's why we learned it in first year. It's what most people think of when they think of engineering in general. Now, areas of interest in these beams can vary. Let's say I can be interested in the shear force function V. I can be interested in the bending moment function M. And typically these two, they're very simple. Very simple. We learned them all the way back in Eng 130 or statics. Not too hard to calculate. We can get a little bit more complex though, because another thing that we need to design beams, deflections. We need to make sure that our beam is serviceable so that the occupants don't, throw up every time they walk on your floor. This one gets a little bit more complex. So to determine things like deflections, stresses, or even strains in beams, it's very common to utilize the Euler-Bernoulli beam assumptions. All right, and there's basically 4 of them. Well, I have 4 of them, but some people lump them into 3, some people lump them into 2. It's basically whatever you want. But basically, here's the assumptions. The deformations are small. Again, in civil engineering aspects, this is usually the case. Unless we're dealing with an earthquake, the deformations are going to be very small. The second one is the beam is made up of a linear elastic isotropic material. Again, in civil engineering applications, we deal with steel, which we know is isotropic and very nice. The linear elastic part, well, under most of the beam's life, it will behave nice and linear elastic until you get into something like an earthquake, of course. 3, the effects of Poisson's ratio are ignored. All right, and this one sounds a little bit more scary, but I'll touch on that in just a second. And the fourth one is plane sections remain plane. So if we look at assumptions 3 and 4 with the Poisson's ratio and plane sections remain plane, these are typically only valid for a slender member. So if we're dealing with a very long beam where the length of the beam is much greater than the thickness, this typically holds very true. It provides a very good approximation. If I were to deal with a really short beam, this does not hold true anymore. So if you guys are designing something very squat or slender like a shear wall, don't use these. These are not good. But for the purposes of this course and the purposes of showing you guys exact solutions, this is great. Because the first thing that we realize when we're dealing with these exact solutions is we need a lot of assumptions to make it work. It's not just here's an exact solution, you're good to go. First thing we have to do is we have to assume a lot of crap. It's not very fun. All right. So let's move on a little bit forward and we say, well, I remember shear and bending moment. This was back from Eng 130. So the first thing we're going to look at is the shear and bending moment of these beams. And to do that, what we're going to do is we're going to take a little section of the beam and analyze the forces on it. So what I did is I cut a little section of a beam, and we know that it has a distributed load Q. All right. So when I cut it, remember, we're exposing those internal forces. Now, it's nothing like the traction vector. That's a bit more complex. We know that for a simple beam, it's going to have 3 different forces. The first one is going to be the normal force N. And what I'm doing is saying on the left-hand side, it's normal force N. And then on the right-hand side, it's N plus the change in N over the distance dx1. We have a shear force, which is V. And then, of course, on the other side, I have the shear force plus the change in shear force over that distance dx1. And then finally, we have bending moment. So again, same thing. We have moment on the left-hand side, and then we have the moment plus the change in moment over that length dx1 on the right-hand side. So these are going to be the sign conventions we also use. Now from here, I can take a nice, easy force equilibrium, and let's say that I do some of the forces in the x2 or the vertical direction. I get V minus V plus dV over dx times dx plus Q times dx is equal to 0. Well, from here I can say, all right, well, those V's cancel out nicely. Therefore, I can cancel the terms and simplify the equation. From here, I can say, oh, hold on 1 second. I have dx1 on both sides. Therefore, I'm going to divide by dx1, and I get the following relationship, where I have a relationship now between the distributed load on the beam to the shear force on the beam, where Q is equal to dV divided by dx. All right, nice and easy so far. Again, we just got a load-shear relationship. This goes back to statics. This is nothing too crazy yet. Similarly, I can look at this and say, you know what? I'm going to take the moment around x3 of this beam. Now, I forgot to show it on the diagram, but I'm taking the moment basically on the left-hand or the right-hand side right here. So I think you guys can see my mouse. I'm going to take the moments about this point over here, and I'll update the lecture notes so you guys can see exactly what I'm doing. So again, I get a nice long equation where I get negative m plus the change in m over dx1 minus v times dx1 minus q dx1 multiplied by dx1 divided by 2. And of course, this is equal to 0. We're dealing with a static case here. All right, now, just like before, I can say, oh, hold on 1 second. Those 2 moment terms, they cancel out. And therefore, I can simplify my nice equation. From here, just like before, I have dx1 terms everywhere. So what I'm going to do is I'm going to divide by dx, and therefore I get the following equation. Now remember that once we did this in the last slide, we had our final relationship. But now if we look at this, we still have a dx1 because above we had a dx1 squared. So if I divide by dx1, well, I'm still left with the dx. Now this is the point where we have to realize that what we're doing is we're trying to prove something. Therefore, what we're doing is we're actually going to take this little slice and we're going to take the limit as dx1 approaches 0. Therefore, this will completely cancel out because it'll go to 0. Therefore, I'm left with my second relationship, which my shear force is equal to the change in moment over dx1. All right, so now I have a shear moment relationship. So from the previous slide, I had a load to shear relationship. Now I have a shear to moment relationship. And this is, again, from statics, but now we're going to take it a step further. Let's start talking about displacements. Like I said, shear and moment, they're easy. We just prove the relationships really fast, nothing too crazy. Displacements or deflections, this is where things get a little bit more complex. So let's say that I have a nice beam just sitting around. The first thing that we're going to do is we're going to define a certain axis. So what we're going to do is we're going to align the x1 axis over the length of the beam, and then the x2 axis is the one that's going to be vertical. All right. So what we're going to do is we're going to place a load on the beam, and the beam is going to deflect. All right, the beam's going to deflect. And what we're going to do is we're going to say that the distance from the original axis x1 to the new centroidal axis, which is that dotted line, that's our displacement function y. This is what we're trying to solve for, is this y right here, the displacement of the beam. To do that, we have to use that plane sections remain plane assumption. This is going to be probably the most critical one in this course, or at least for Euler-Bernoulli beams. So let's analyze 2 points on the beam. So they're the exact same point on the beam. One is just before the deflection occurs, and the other one is after the deflection occurs. So what I'm going to do is I'm going to draw a horizontal line straight up from this cross section. And as we can see, this horizontal line crosses the neutral axis of the deformed cross section. All right, so there's kind of one of the assumptions again that we make for Euler-Bernoulli beams. Now we can see though that the point actually shifted a little bit to the right. All right, or I guess to the left. Sorry, I don't even know my directions. So now we're going to try and quantify where this new point is located in reference to its original coordinate. All right. So to do that, we have to utilize the plane sections remain plane assumption. Therefore, that this blue section right here is perpendicular to the neutral axis. Well, we're saying that's the same case up here, where this blue line or this cross section is going to be perpendicular to this new neutral axis. And because of that, we can actually create ourselves a nice triangle. All right, so again, our neutral axis would be right here. We have half of the beam's cross section, x2, going up over here, and we have an amount it is rotated by theta. Now, if we look at this, we just see it's a nice right triangle. Therefore, on the top, we have x2 times sine theta, and at the bottom, we have x2 times cosine of theta. Now, since we have this, we can then create something very important, which we discussed this morning, which is the position function of the beam. All right, so this is going to be the whole key here. So after the displacement, we can find our position function. So our first one is the x1 direction, so the u1 direction here. And we know that this is going to be x1, which is the distance from our axis over here, all the way to this dotted line, this vertical dotted line. Now, we know that the point actually shifted a little bit to the left by a magnitude of x2 sine theta. So therefore, we have x1 minus x2 sine theta. So this is going to be our position function right here. Our second one, if we were to look at the vertical direction, we can see that it shifts up by a value of y. So the value of y is going to be from our axis here up into the neutral axis right here. So I'm at this point right here. And then it also shifts up by this amount right here, x2 cosine theta. So we're going to have y plus x2 times cosine theta. And then our third direction, x3, it doesn't change. That's the in-depth thickness. It doesn't change. We're assuming symmetric bending. All right. So from here, this is the hardest part. Once you guys have the position function, we know it's basically just plug and chug our way all the way to the strain tensor. So the first thing we're going to say is, well, we assume small deformation. Therefore, those sine theta and cosine theta, they can actually be approximated as follows, where cosine theta, that's approximately equal to 1 for small deformation, and sine of theta is approximately equal to just theta. So what I'm going to do is I'm going to substitute those nice new things into there and say, all right, well, now I have a nice, simple position function. Now you guys remember, why do we calculate the position function? Well, we did that so we can calculate the displacement function u. So u, it's very simple. It's simply our position function small x minus big X. So I'm going to take that position function small x. I'm just going to minus x1, x2, and x3 from it. And I'm left with the following, where my displacement function is negative x2 times theta, y, and then 0. So it looks pretty good so far. And we can actually make one final adjustment to this by saying, well, this theta, this is the rotation of that neutral axis. Basically, it's the rotation of the beam. Now we know that the rotation of the beam is simply going to be the derivative of the deflection function with respect to x1. Basically, it's the change in height over the change in length. Nice and easy. So from there, we can actually start calculating strains. All right, so this is where things start to get fun. And this is why we had to do a little solid mechanics review before we get into this. So now that we know the displacement function, we can determine the displacement gradient. So we have u, which is equal to negative x2 times theta. But again, we said that theta is equal to dy over dx1. The second component is simply going to be y, and then the third component is going to be 0. Now, our displacement gradient nabla-u, it's that big ugly thing with all the partial derivatives. But if we look at this now, and since we have our displacement function, all we need to do is take partial derivatives of everything. So it gets actually pretty nice and easy. The one thing that we're going to have to keep in mind, though, when we're taking these partial derivatives, it's always with respect to something. So sometimes it's obvious. If I were to look at u1, I have an x2. Therefore, I know how to take the derivative of that with respect to x2. Nice and easy. But if I were to look at y, and I'm taking the derivatives of that, well, I need to know what y is a function of. And basically, y is that deflection, which is a function over the length of the beam. As I go over the length of the beam, the deflection is going to change. So the thing to keep in mind here is that y is a function of x1. Therefore, I can take the derivative of y with respect to x1. And because of this, I'm left with the following strain tensor. And it's actually, displacement gradient. And again, we have to use this y as a function of x1 in things like this. So our first thing here is the partial derivative of u1, which is this component here, and we're taking it with respect to x1. So since y is a function of x1, we take the derivative of this whole thing yet again, which is why we get the second derivative of y with respect to x1. Now, if I were to look at the second component, I'm taking the derivative of u1, which is this first component up here, but this time I'm taking it with respect to x2. So in this case, I have my x2 here. This just goes to 1. So therefore, it's negative dy over dx. And I had a great question here. Can you explain again why y is a function of x1? Well, if we look across the beam, we can see that as we go across the beam, so as x1 changes, the deflection of the beam changes too. So hopefully that makes sense. Hopefully that makes sense to you. Did I clear that up? As we go across the beam or change x1, the deflection changes in the beam. It doesn't remain constant. All right, perfect, good to go. So we'll continue on. So from here, good to go. Finally, our second row here, we're taking the derivative of u2 with respect to x1. So since, again, y is a function of x1, we just take the derivative of it, and then the rest are all going to be zeros. Nice and easy. So again, why do we calculate this displacement gradient? Well, we want that strain tensor. So we said that our small strain tensor is simply going to be 1/2 of nabla-u plus nabla-u transpose. I add those all together, I get the following. Where basically, my only non-zero strain component for these Euler-Bernoulli beams is going to be the strain component epsilon 1,1. Now, if we look at this one too, we can see that as x1 is constant over a cross-section, the profile is actually going to be linear. We have a nice linear strain profile. And if you guys have ever taken steel design or concrete design, anything like that, that linear cross-sectional strain profile is where all of our equations basically come from. So it's going to be very important moving forward. All right, so you guys may be saying, Clayton, why do we calculate the strains? Well, remember that because of constitutive laws, if we know the strains, we can figure out the stresses. So from a strain tensor, it's easy to see that there's also a stress component, sigma 1,1. Makes sense. If we have a strain component in the 1,1 direction, we must also have a stress component in the 1,1 direction. So in order to find the stress component, we're going to use our constitutive law as well as ignore Poisson's ratio. So again, another assumption that we have here. So if that's the case, then we basically have a uniaxial case, which is Hooke's law, where sigma 1,1 is equal to the Young's modulus times epsilon 1,1. Now, if we look at epsilon 1,1 in there, well, we just figured out what that is in the previous slide. It's negative x2 multiplied by the second derivative of that deflection function. All right, so this is where we come from, and then we can actually simplify this once again into sigma 1,1 is equal to the negative moment function times x2 divided by I. And you guys are thinking, hold on, well, I understood the first step, but that second step, where'd that come from? Well, we'll show this later on in the next slide, so don't worry about this too much. I only highlighted it here because when we're calculating stresses in beams, this is the equation that we're going to get into. All right, so one of the problems with our assumption, though, or the Euler-Bernoulli beam assumptions, is that we actually predict zero shear stresses, which we know is not true, because in linear elastic materials, a shear stress is proportional to the shear strain. And since our shear strain is zero, it's basically saying that there's no shear stresses. However, we know just by the mechanics of the beam that we have a shear function across the beam. And since we have a shear function, well, there obviously must be some shear stresses. So in order to find shear stresses, we utilize the relationship between shear stress and shear flow, which you guys have learned in mechanics and materials. Fairly simple. All we need to realize is that our shear stress component, sigma 1, 2, is going to be equal to negative V, where V, of course, is our shear function, times by Q, divided by IB. Now, I is the moment of inertia of the beam, very simple, and B is the depth of the beam into the page. So the depth of the beam into that third direction. So if we were to look at that, shear, no problem. Moment of inertia, no problem. B, no problem. What about Q? Q is the only real tricky part. However, since we aligned our axis with the centroidal axis of the beam, we can easily find Q by taking the following double integral, and we get that Q is equal to B times T over 2, where T is the height of the beam, or the thickness of the beam divided by 2, minus x2 multiplied by T over 4 times x2 divided by 2. Now, if you look at this, it definitely looks confusing. The shear stress component, it's going to be the most confusing part, but I'm going to show you guys exactly how we input that in the code so you guys know exactly how to do your assignment, all right? So from there, we're going to go on to moment deflection relationship. Remember that at the very beginning, we found a nice relationship between the load, the shear, and the moment. And now we just found a nice relationship between the displacement, the stresses, and the strains. So now what we're going to do is we're going to try and bring it all together. So we realize that we can actually calculate the moment of a cross section by taking the double integral of the stress multiplied by the distance x2, which makes sense. All we're doing is we're taking the forces on that cross section and multiplying them by their moment arm. Very nice and easy. And from here we say, oh, hold on a second. I know what that sigma 1,1 is. I can relate it to strain. Therefore, I substitute my value of sigma 1,1 in terms of my stress, in terms of my strain, which was actually in terms of the deflection function, and I get the following. Now, if we look at this, we say, well, hold on one second. I'm differentiating with respect to x2 and x3. Basically, I'm differentiating within the cross section of the beam. Now, we realize that the deflection does not change over the cross section. It just changes with respect to x1. And same with the Young's modulus. That's just a constant. Therefore, I can bring out y as well as e outside of the integral to give me the following, where the moment is equal to e multiplied by the second derivative times the double integral of x2 squared dx, dx2 dx3. All right. Now, for those of you geniuses out there, you guys saying, oh, hold on one second. I know what that double integral is equal to. That's simply the moment of inertia of the beam, and you guys are exactly correct. Therefore, we can get the following relationship between moment and deflection, where our moment is equal to EI multiplied by the second derivative of deflection. Now, this is great because remember at the very beginning when I was talking about that static stuff, we had a nice relationship between load and moment. So therefore, I can utilize the relationship where Q is equal to the derivative of shear, which is equal to the second derivative of moment, which is now equal to the second derivative of the expression on the left. I get the final equation where Q, which is my load, is equal to EI multiplied by the fourth derivative of the deflection function. All right, so this is what's going to be great for us. Because if you guys think about it, if we were designers analyzing a beam, what do we know? We don't really, well, we can figure out the shear and the moment function, we can, but that's extra steps. If I were to just get a beam for the first time, I guarantee I'll have the beam and I'll have the load on the beam. Now, this is great because I have an expression that relates that load I was just given to the deflection of the beam. All right, so when we're dealing with an Euler-Bernoulli beam analysis, we basically have three steps. The first one is we're going to determine the deflection function of the beam from the applied loading. So we know what Q is. Q is that distributed load, and we can solve it with we can solve the deflection function. So right now we're solving for y. All right, so this is going to be the first step. Now that we know what y is, what our deflection function is, we can now determine the shear and the bending moment function because they are just functions of y. So once we know what y is, we can figure out both m and what v is. And these are going to be a function of simply x1. And from there, since now I know what the moment and the shear is, well, I can find those stress components. Because if we look at sigma 1, 1, it has the moment function, which we just solved for. If we look at sigma 1, 2, it has the shear function, which we just solved for. Now, finally, the last thing I just want to say for these ones is these ones are going to be a function of x1 as well as x2. So these ones are going to be a little bit different when we go to plot them. All right, so that's going to be the analysis. And with that, that's going to be the end of kind of the lecture. So let's get into an example. I don't know about you guys, but I always find examples are the best way to kind of figure out what's going on. So what I'm going to do is I'm going to pull up eClass here, and we are going to look at the assignment just to see what you guys think. So we're going to open this in the new tab, and we're going to go through the assignment. So if we look at the assignment that's due next week, it's 2 questions, and initially it looks really, really bad, but it's actually very simple. So the first one, we have a beam. I give you what the distributed load is, as well as cross-sectional properties, as well as the Young's modulus. And all the first question wants is the deflection function. We gave you a nice relationship between the load and the deflection function. Therefore, all you guys are going to have to do is solve that differential equation. Nice and easy. Or is it? We have a problem right here because we have a distributed load right here. Now, the problem with that distributed load is it creates a discontinuity. Remember that differential equation, we're assuming everything is continuous. Therefore, the first question, it's actually really simple. We're just solving that differential equation. But the only difference is we're going to have 2 equations. One is the deflection function from 0 to 4, and then the second one is going to be the deflection function from 4 all the way to 6. And the reason why is we have that discontinuity there. All right, so that's going to be the first one. The second one is, again, more beams. I told you the whole assignment's going to be these Euler-Bernoulli beams, and it's very simple. All we're going to do is we're going to analyze a simply supported beam. So I want the deflection, I want the bending moment and the shear force, as well as the stress components sigma 1, 1, sigma 2, 2, sigma Vm, and the hydrostatic stress. All right, so this sounds like a lot right now, but basically we're going to go over this first one together. So if we look at question 2, we have to do this analysis for a simply supported beam, as well as a fixed ends beam, and then compare them. And this looks like a lot of work, but what we're going to do together as a class right now is we're going to go over a simply supported beam, how to code it. And if you guys code this correctly, then you guys will be able to figure out the fixed ends beam in about 2 seconds. So it's all about writing some good code. All right, so I'm just going to minimize this. I have a little sheet here of, I guess we're doing the fixed ends beam, not the simply supported beam. And we're going to go into Mathematica to solve this together. Oh, sorry, guys. So for those of you guys who aren't familiar with Mathematica, I know a lot of you are, but a lot of you aren't. It's very simple. All we're going to do is we're going to go new document, and we're going to give it a nice new window. Now I'm just going to type something just so I can zoom in on it really quick. So how's that for viewing? Can you guys see everything okay if I were to write like that? Everything look fine? Hopefully. Oh, I got a thumbs up. Awesome. Perfect. So when I'm dealing with these beams, and don't worry, whatever code that I create right now, I will post to eClass. So if you guys want to use my code for the assignment, go right ahead. As long as you guys know what's going on. That's the important thing, is we figure out what's going on. So actually the first thing I'm going to do is I'm going to clear all parameters. So clear global star. So this basically just clears all parameters every time I input something. It's nothing too special. So the first thing I'm going to find is the parameters. All right, so if I look at my beam here, I have a fixed ends beam, has a load Q and a length L. So I see that my parameters are as follows. I have L, which is equal to 6 meters. All right, so one of the key secrets I'm going to give you guys, and this can be very important once we start talking about finite element and more specifically abacus, is we need to keep units consistent. So for me, I always go millimeters, newtons, and MPa. If I do that, everything will always be consistent and work out. So if I'm going with millimeters, well, of course, 6 meters is 6,000 millimeters. All right, so I go down. I can define now my Young's modulus as 20,000 EPA, 20,000. So one of the things that you guys may have seen right now is that when I defined L, it's blue. And what that means is that it's undefined. It's good to go to be stored as a variable. If I define E right now, it's black, meaning that it's already defined in Mathematica. So I cannot use E as a variable. I'll get a problem. So what I need to do is I need to think of another variable name. So what I do is I just go EM, which basically is the elastic modulus, for me anyway. Now that it's blue, I'm good to go. All right, so next one I got B, which is the height of the beam. I know that that's 500 millimeters right here. Nice and easy. Oops, I don't know where I clicked. 500. And then finally, I have H over here. So I'm going to go H. This one's going to be equal to 800. So those are the simple ones. Now the next one is Q. So I'm going to go Q is equal to, and if I'm keeping it consistent with the scheme of newtons, millimeters, and MPa, do I need to, what conversions do I need to do to Q? I have it as 25 right now. Do I need to times by 1,000? Do I need to divide by 1,000? What do you guys think? If I'm keeping my units consistent. Leave it the way it is 25, 25,000. Divide by 1,000. All right, so I see times by 1,000, divide by 1,000, so that just leaves it the same. Divide by 100. We actually just leave it the same. Because if you think of the kilonewtons, that adds 1,000, but then the millimeters divides by 1,000. So Ismail is correct. We times by 1,000, then divide by 1,000. We're left with just 1. So 25, it just stays the same. So that's a little fun fact. Kilonewtons per meter is the exact same as newtons per millimeter. Little fun fact here. Now, something that we'll also see is that this is actually wrong. And the reason why is when we started deriving all these equations, remember that we assumed that Q was going upwards. But if we look at our actual scenario for the beams, Q is actually going downwards. So we need to include a negative sign to indicate that we're dealing with a distributed load that's going downwards. All right, so that's going to be our parameters really quick, and that should be a nice, easy part for you guys. Now, when it comes to you guys implementing your own parameters for the assignment, if you guys have this code, it's easy. Just swap the parameters. You guys are good to go. All right, so now that we have the parameters, we said that the first thing that we do when we analyze these beams is we have to solve that differential equation for y. So we look right here, our deflection function y is governed by this differential equation, where Q is equal to EI multiplied by the fourth derivative of our deflection function. Now, the reason why we love Mathematica so much is it's actually able to solve differential equations for us nice and easy. So I'm going to just type in differential equation, showing you guys what exactly my steps are. And the first thing I like to do is I like to just define what that differential equation is. So I'm going to go dE, which is differential equation, is equal to EI times the fourth derivative of the deflection function. So I'm going to define my deflection function as y, and if I'm doing a derivative in Mathematica, it's just prime. And since I'm doing 4 derivatives, 1, 2, 3, 4, and then this is going to be a function of x1. Now, what I'm also going to do is I'm going to take this q over here and throw it to the other side to make this function equal to 0. So I'm going to go minus q. All right, but now we have a problem, because if we look right here, EI is not defined. We haven't defined what that is. So one of the things I'm going to do is I'm going to come up here. I'm going to go, first of all, I'm going to define my moment of inertia. If I have a square rectangular beam with a base B and a height h, what is the moment of inertia for a rectangle? What do you guys think? Moment of inertia of a rectangle. All right, you guys all got it. That's exactly correct. So we're going to go base times height cubed. Oops, cube divided by 12. All right, and now that I have my moments of inertia as well as my elastic modulus defined, I'm simply going to go EI is going to be equal to EM times IG. All right, so now when we get to this part of the equation, this will be defined. I have my Q also defined. The only thing that's not going to be unknown is this Y prime, basically. All right, so the first thing I do is I define what my differential equation is in Mathematica. Second thing I'm going to do, I'm going to solve it. So what I'm going to do is I'm going to go sol, which is basically the solution of my differential equation is equal to. And if I'm solving a differential equation in Mathematica, there's a specific function called dsolve. So dsolve, S-O-L-V-E. As we can see, it turned black, which means that it's defined. So if you guys have it as blue, it means that you guys probably spelled it wrong, something like that. And when we're dealing with a function in Mathematica, we have square brackets. And basically, this is the function, and everything inside the square brackets is what we input. Now, when we're dealing with a differential equation, or solving a differential equation in Mathematica, we have 3 arguments that we need to input. And each argument is separated by a comma. So I'm going to go comma, comma. Right here, I'm going to have my first argument, my second argument, and my third argument. Now, the second and third arguments are actually really simple. The second argument is, what are you trying to solve for? What equation are you trying to solve for? Well, we already know that we're trying to solve for y as a function of x1. That's the whole goal here. We want to find out what that deflection function is. The final argument, the last one, is what variable are you guys using? Well, we know that y is a function of x1, so I'm just going to put in x1. Okay, so that's basically it. This right here, that first argument, this is where all the fun is happening. This is saying, what are you trying to solve? Well, we want to solve our differential equation above. So I'm trying to solve my differential equation when it's equal to 0. Because again, since I moved this q to the other side, we know that this equation is equal to 0. So what I do is I say my differential equation is equal to 0. So basically, the equation above is equal to 0. I want to solve for y, and it's a function of x1. All right, so that's all I did so far. And when I do this, I'm going to run the code now. And then to run a code in Mathematica, you hold down Shift and then press Enter. So I'm going to go Shift, Enter, and I get this right here, where my solution right here, y1 is equal to x1 to the power of 4 divided by a big number, plus c1 plus x1 c2 plus x1 squared c3 plus x1 cubed c4. My question to you guys is, what do you think these c's are? What do you guys think? I just solved the differential equation, and it gave me 4 coefficients. Why couldn't I just get my equation right away? What's the problem that I'm having when solving a differential equation? Anyone want to be bold? Integration constants? Yeah. So yeah, boundary conditions. Boundary conditions. You guys are all correct. So if I look at the beam here, I can see that both ends are fixed. And this is where the key is going to come into that assignment, because if I were to look at the assignment and look at question number 2, where I'm comparing the first beam, the simply supported beam, to the second beam, they are the exact same in every way except for those boundary conditions. So when you guys write the code for, let's say, the fixed end beam, if you guys write the code good for the fixed end beam and you guys want to go to the simply supported beam, all you guys are going to have to do is modify the boundary conditions. Nice and easy. All right? So minimize this. So the question becomes, how do I implement boundary conditions? Well, it's actually very simple. Everything will always go into this first argument there. So since I'm inputting multiple arguments, what I do is I put little squiggle brackets around it. And since I put squiggle brackets, I can go comma and then write another argument, comma, write another argument, etc. All right, so if I'm looking at this beam and it's fixed end, well, let's look at the end where x1 is equal to 0. So what I'm going to do is I'm going to go y of 0, so the deflection at 0, well, we know it's fixed. Therefore, it's going to be equal to 0. All right, so there's one of them. If I were to look at the other end of the beam, where x1 is equal to L, so I'm going to come over here, go comma, y at L, well, we know that the deflection at this end is also going to be equal to 0, right? Makes sense. Both ends are fixed. There's no deflection. So if I were to go to here now and run the code, and I forgot to, oh, no, I defined what L is. If I were to run the code now, I get this, but I still have a problem. I have C2 as well as C3. So 2 of the constants disappeared, but I still have 2 left, which basically means that every constant that's in there, I need 1 boundary condition. So since I had 4 constants, I need 4 boundary conditions, but I only specified 2. So my question to you guys, what are the other 2 boundary conditions for this fixed end beam? I've already did the 2 displacement ones. What else do I have to utilize for a fixed end beam? The slope at the ends is equal to 0. Any other takers? Velocity, we're not going to get into velocity here, but yes, we're right in that first derivative of the deflection function, so y prime, which is the rotation or the slope, we know that that is equal to 0 at the fixed ends. So how do I do that? Well, I simply go comma, because I'm going to add another boundary condition. I'm going to go y prime at 0. That's going to be equal to 0. And I'm going to go comma, y prime at L. This is going to be equal to 0 as well. All right, so now I have my 4 boundary conditions. I have 2 right here for my displacement, and then I have 2 right here for my rotation. Now, one problem that a lot of students tend to have when they first use Mathematica, when we're doing these equations, when something is equal to something in these equations, we do the double equal sign. So please don't forget that. If you guys just go equal to, well, then it's thinking you're trying to store a variable, which will start to create a lot of problems. So if I were to run this now, I have my deflection function as follows right here. Nice and simple, right? Use my Mathematica command. I have my deflection function right here. But notice that when I go sol right now, so I'm going to suppress this. And if I were to write the variable sol, which I defined above, I don't have just the equation. I have y is equal to this equation. So what I'm going to do is I'm going to now define my deflection function. And I'll go down. Actually, I'll go down here and go deflection function. So when I want my deflection function, I want it just to be equal to this part right here. I don't want this little part up here. This will create some problems. So what I'm going to do is I'm going to go y, which is my deflection function, is going to be equal to y of x1, basically when solution of 1. All right, so this is kind of hard to explain out of the scope of this course, really. But if I run this now, oh, recursion limit, what did I do wrong? Y of x1 when sol of 1. Oh, I did the. So this is another thing too. Mathematica, if I do single square brackets around something, it means I'm trying to do a function. Double square brackets. Again, I'll be posting this code, so you guys just need to really modify this code right here. So now this is great because I have my deflection function right here. Now, what did we say after our deflection function? We can find our bending moment and our shear function. So I'm just going to suppress this. I'm going to come down here, and I'm going to go, let's go shear and moment. Now, we'll start with shear, which I'll define as V. We know that V right here is equal to EI multiplied by the third derivative of our deflection function. We already have EI defined. We did it up here, so we're good to go. All we need now is the third derivative of our deflection function, which is easy because we have our deflection function. So in Mathematica, there's a very nice function for derivatives, and it's simply just d. Very unoriginal, but it's there. So d, and again, since it's a function, it has those square brackets. Now, this function is going to take in 2 arguments. So I'm going to put a comma. I'm going to have 1 argument here, and then I'm going to have a second argument over here. The first argument is, what is the equation you want to differentiate? Well, we know that we're differentiating our displacement function y. All right? Displacement function y, good to go. The second argument is, what is the variable you want to differentiate with respect to? Well, we know it's going to be differentiated with respect to x1, right? But now the only problem is if we type this in right here, all we did is take the first derivative, but we want to take that third derivative. So in order to specify how many times you want to differentiate, what we do is in our second argument, we put our squiggle brackets, we define the variable which we want to differentiate, and then we specify how many times. So for the shear function, we want to differentiate 3 times. So I'm just going to go 3, right? Nice and simple. And if I were to run that, I have my shear function. Now my shear function, as we can see, it's a linear shear function, which makes sense. If my load is constant, my shear is going to be linear. From there, I can do the same thing for my moment, because we know that the moment, and I'll scroll down here, is equal to EI multiplied by the second derivative of our deflection function. So we're going to have EI multiplied by the derivative of our deflection function y with, one more squiggle bracket than necessary, with respect to x1, and we're doing this one specifically twice. So if I run that now, I see that I have my moment function, and it is now a function of, or it's cubic. No, cubic. I'm an idiot. This is quadratic, all right, which makes sense. It's 1 higher order than the shear function. All right, perfect. So now that we did those 2, we can go on to the stress components. And one thing I want to emphasize really quick, actually, before we do that, is if I were to show both the shear as well as the moment, we can see that they're just a function of x1. Okay, so when we plot these, they can just be plotted as just a regular plot. It's nothing too crazy. They don't vary over the height of the beam. So now what we're going to do is we're going to get into stress components like this. And we see, all right, well, if I'm looking at sigma 1, 1, it's simply m times x2 divided by I. All right, so I go, let's say S11, sigma 1, 1. This is going to be equal to negative m. Remember, our moment function, we already defined it, so it's good to go, times x2, so just times x2, and then finally divided by I. Oh, well, we also know what I is. Therefore, once we get to the stress components, it's just plug and chug. There's really nothing you need to do. So if I were to run this now, I have my stress component, and if we look here, it's a function of both x1 as well as x2. All right? Now let's say that the stress component function is something that you guys want to show as a final answer. And you guys are thinking, oh, this looks pretty ugly. All it did was substitute the variables. Well, all we can do is we can go / full simplify over here. And if we were to run it, it tries to make it a little bit nicer. So it's just one of those fun things in Mathematica. If you guys want to try and simplify something, you guys can go / full simplify. We can take it further. We can go / expand. So as we can see, some terms are in front of the other. We can do that. We can simplify it like this. So these are just some things to make your answers nicer if you guys want to. All right. So if we look next, we can see we want the stress component sigma 1, 2. So we go S1, 2 is going to be equal to negative V. So negative V, where we defined V above. So we're good to go for V times Q, and then divided by I times B. So if we look at I, well, that's our moment of inertia. We define that. We times by B. Well, that's just the thickness of the beam right here, which we've also defined. The only thing that we haven't defined here is actually going to be Q. All right, so before we actually run this, we need to define what Q is. So we're going to have Q is equal to, and we have a nice equation for Q over here. So Q is going to be equal to B times, and then in square brackets, this T right here, that's the same as the height of the beam. So this is just going to be H over 2. And I like to put a lot of brackets. You guys are probably cringing at how many brackets I put, but that's okay by me. I'd rather be safe than sorry. Times x2. And then what we have is we have H over 2 plus x2 divided by 2. All right, so now that I have Q defined, I can run this function down here. I get my shear stress component right here. So looking pretty good. I have all the components I need to solve for everything. Now, I've showed you how to do every single thing in the assignment except for the von Mises stress. But you guys have a nice formula for the von Mises stress. All you guys need to do, now that you guys know what sigma 1, 1 is and sigma 2, 2, just substitute it into the formula. You have your von Mises stress. So it's going to be very simple. Last thing I want to do is just to plot these functions, because that's one thing that'll help you visualize what exactly the difference is going to be. So I'm going to come down here, plot functions, and we're just going to take a peek what they look like. So if I'm plotting something in Mathematica, it's actually going to be very, very easy. The command to plot something, plot. Nice and easy, right? Just go plot, and it's going to take in 2 arguments. So I'm going to have one comma here. The first argument is what function do you want to plot? So let's say I want to plot the deflection. Well, I know that that function is going to be y. And then the second one, of course, is going to be what is the variable and what are the limits? So what I'm going to do is I'm going to go squiggle brackets, and the first thing I'm going to say, well, I want to plot this over x1. I want to plot it over the length of the beam. Now, the length of the beam goes from 0 all the way to L. So just like that. And if I were to run this, I now have my deflection function for the beam, which makes sense. This is exactly what you would expect for the beam under these loading scenarios. Now, let's say that I forgot that Q was defined as going upwards. Let's say I just put Q is equal to 25. This is where the plot kind of saves your ass, because if I were to plot this, well, then I get my beam does this. And I can say, oh, hold on a second. The beam's definitely not going to deflect upwards. Therefore, I probably have a problem with Q. So I'll switch that back, go like this. Now, by default, Mathematica will always try and plot things in kind of a square fashion. So what I like to do to try and make it look like more like a beam is I add a third argument, which is called the aspect ratio, and I usually set it to 1/4. So if I do that, the aspect ratio of the graph decreases. It looks a little bit more like a beam. Now I can do the same thing for the shear and the moment. So I'm going to just plot twice more, but instead of plotting my deflection, I'm now going to plot my shear. and now I'm going to plot my moment. So I'll do those in, I'll run them. I now have my shear. And again, the values are big because I kept everything in newtons. So this is 50,000 newtons. So it's only 50 kilonewtons actually. And same thing for moment. So this is in newtons per millimeter. So if I want actual engineering things, what I do is I go shear. Well, if I want it in kilonewtons, I divide by 1,000. Moment, if I want it in kilonewtons per meter, I divide by 1,000,000. So now if I run it, it looks a little bit more realistic, of course. So these are the easy functions to plot. And the reason why, they're just a function of x1. I just vary x1 throughout the equation. Now, the last thing that we're going to just cover real quick before the end, and again, don't worry, I'm going to post the code. You guys can use this code for your assignment. No big deal. Is the shear stress ones, if we're trying to plot those, because they're a function of x1 and x2. So we can't just do a simple line plot. We have to do a contour plot. So what I'm going to do is go contour, just something like that. So when we're doing contour plots, it's actually going to be basically the exact same as above. The only difference is we're going to have two arguments. So what we're going to do is we're going to type in contour plot. It comes up. And this is how we're going to plot the stress functions. We're going to want the contours. Basically, how does the stress vary over both the length of the beam as well as the height of the beam? So this one's going to take in 3 arguments, unlike the previous one, which took in 2. So I'm going to add 2 commas. The first one, of course, what is the function you want to do the contour plot of? Well, we know we're going to start off with S11. All right, nice and easy. The second one is, what is the horizontal component? Well, we know that the horizontal component is x1, and this goes from 0 over the length of the beam. Right, nice and simple. The second one over here, what is the vertical component? Well, the vertical component we know is x2, and since we defined the axis as at the centroid of the beam, we know that this goes from negative h over 2 to h over 2. Because again, in the slides, we defined our axis going through the center of the beam. Our axis is not at the bottom of the beam, it's actually at the center of the beam. All right, so if I were to run this, scroll all the way down, I now have my contour plot of the stresses. So what I'm going to do really quick is I'm just going to add in that aspect ratio just to make it look a little bit nicer. So these are my contour plots. And this makes sense. We can see up here that we have compression at the top of the beam in the midspan, and we have tension at the bottom. Makes sense. Near the supports, we have compression near the bottom and tension at the top. Makes sense yet again. So that's how we basically plot them. Again, once you define one, it's easy to go to the other. So I just go comma. Instead of S11, I can plot S12. Same thing. Come down here. Oh, taking its sweet time. Oh, I forgot to put in the bracket at the end. My mistake. And then we get S12. All right, so that's basically it. That's how you guys do the first assignments, and I will post code. So for when you guys do the assignments, I will give you guys Mathematica code. All you guys are going to have to do is alter it for your specific thing. So I'm going to come up here. The only difference between these two beams, once you input the parameters, change the boundary conditions. Boundary conditions here, it's fixed. Boundary conditions here, simply supported. Shear force, already coded. Bending moment, already coded. Deflection, already coded. Sigma 11, sigma 22, already coded. The only thing you guys need is the von Mises stress and the hydrostatic stress, which is nice and easy because you guys have the complete stress tensor. It's just sigma 11 and sigma 12. The first one, even easier. All I want in this one is the deflection function. And again, we're going to have 2 of them because of this discontinuity. So before we end really quick, I know that time is up right now. I just want to ask you guys, and this will probably help. How do we take into account this discontinuity? What do you guys think? This will be the key to question 1. How do we take into account this discontinuity in our calculations?
Do you solve the differential equation from 0 to 4 meters and then from 4 to 6 meters?
Yes, that's completely correct. So what happens is if I'm looking at 2 differential equations and I'm looking at the boundary condition right here, I'm going to have a boundary condition between the 2 differential equations. Now, if we look at the 100 kilonewtons, this creates a discontinuity in shear. Therefore, my boundary condition on this side will be my shear minus 100. No, sorry, my shear is equal to the shear on this side minus 100. So this goes into the boundary conditions. That'll be kind of the hint for this one. Now, if you guys really want, I will post, I did a similar question like this for the undergraduate class, and I can post the how it's done. So I'll show you guys how this is done. Again, I don't want you guys stressing over these assignments. They should be nice and easy for you guys. But yes, we model this discontinuity through the boundary conditions. So that's it. Hopefully assignment 1 should be nice and easy, and I'll post the code right now so you guys can just copy paste and do whatever you want with it. All right, guys, that's it for this lecture. And again, this was probably the longest, the worst lecture possible because of solid mechanics review, but you guys are done now. Now we're getting into the fun stuff of the course. So thank you guys for sticking around through all the the theory. I'll be here if you guys have any questions.